So many thanks to Christoph Külske. He's a member of our Faculty of Mathematics here in Bochum. I learned 2 days ago that the title Gilliarde is the meaning of an athletic dance characterized by leaps, jumps, hops, and other similar figures. Many thanks to Christoph Külske. So I hope you can hear me. Ladies and gentlemen, I'm Peter Eichelsbacher, the chair of this opening session. And it's my great pleasure to welcome you to the World Congress in Probability and Statistics, which is the Bernoulli and which is the IMS World Congress. Welcome to Bochum. Welcome to the Ruhr area, which is a small river, Ruhr, and welcome to the middle of Germany. Welcome on this campus of the Ruhr University. This university was funded in 1965, almost 60 years ago. Thanks for coming. You see me delighted. A world conference. Together we will enter a week of intensive exchange, scientific exchange. You have the opportunity to listen to a great number of presentations, choosing from a total of 600, almost 600 talks and 100 posters. You can listen to many scientists, and I encourage you to reward their achievements by attendance. I thank all speakers in advance for their contributions, knowing that you have made special efforts for great presentations here in Bochum. And I wish all of us an exciting meeting, but before we start with mathematics, which is the main idea, before we will start with mathematics, we will have some opening messages and some more informations from the chair of the local organizing committee, Harold Dehling. And we will have some more music. And this pipe organ is an instrument which is unique in the Ruhr region in terms of its tonal dimension and technical features. Was designed and manufactured by the organ builder Johannes Kleis from Bonn and installed and voiced in this auditorium maximum between February and September 1998. It has 82 sounding stops, registers, and approximately 6,400 pipes. Unbelievable. Please start counting. Now, oops, das sieht man auch. Verdammt. You understand German? Okay, sorry. Und das dann auch noch. Aha, was ist los hier? Sorry, I don't like this. Warum ist die Anzeige nicht Vollmodus? Better. So now I like to leave the floor for the vice rector of our university. Welcome to Günter Meschke. He is the vice rector for research and transfer. He is an engineer with a chair of structural mechanics. The members of the local organizing committee and the members of the Faculty of Mathematics like to thank all the members of the Rectorat supporting us to be able to host the World Congress. Thanks very much indeed. The acting Rectorat is supporting mathematics forcefully. Thank you. Please, Günter Meschke.
Thank you, Peter. Dear President of the Institute of Mathematical Statistics, Professor Kozarok, dear President of the Bernoulli Society, Professor Panaretos, dear co-chairs of the Scientific Program Committee, Professor De Legel and Professor Ramanan, dear Professor Dehling, and colleagues from the local organizing committee, dear colleagues, ladies and gentlemen. On behalf of the Rectorate of the Ruhr University Bochum, it's my great pleasure today to welcome you to Bochum, to the Ruhr University, and to the 11th World Congress in Probability and Statistics, which is obviously a major international conference in the area of probability, theory, and mathematical statistics. I'm excited, as you can imagine, that the Institute for Mathematical Statistics and the Bernoulli Society have jointly chosen this year the Ruhr University and Bochum as the host of this very important conference, which for the first time comes to Germany. This is, from the viewpoint also of the Rectorate, an impressive testament for the outstanding reputation that our scientists in the Faculty of Mathematics enjoy in the international scientific community, and certainly also a sign of trust that the local organizing committee is, so to speak, can be successful to organize such a big event. Having organized a couple of international conferences myself, however, on a smaller level of number of participants, I only can imagine the enormous efforts which are connected with organizing such a conference, which start already probably more than 1 year in advance. And I would like to take the opportunity here to thank Professor Dehling as the chair of the local organizing committee, but also my thanks go also to all members of the organizing committee, and not least to the large number of, to the very large number probably, of people and the team behind the scenes, which is necessary to do that enormous work. And my thanks go also to the co-chairs of the scientific committee, Professor De Legel and Ramanan, for setting up jointly with their scientific committee, with their colleagues from the committee, for setting up such an impressive scientific program. Internationally visible cutting-edge research in the field of probability, theory, and mathematical statistics has a long tradition at the Ruhr University, Bochum. And I can say it belongs to the most successful scientific areas at our university. Not only at our university, but also beyond, in the entire University Alliance Ruhr. This alliance is formed as a strategic unit between 3 universities in the Ruhr area, which is the University Duisburg-Essen, the Technical University of Bochum, and the Ruhr University Bochum. And it is formed, and it has been formed, to join forces to exploit synergies and also complementary competences of the strong teams in these 3 universities. And the scientific strengths generated by joining forces from the faculties of mathematics in Duisburg-Essen and in Bochum, and also from the Faculty of Statistics at the Technical University in Dortmund, is evidenced by a continuous series of collaborative research centers and research training groups, which are the flagships of the German Science Foundation. An outstanding, most recent example is the Collaborative Research Center Spatio-Temporal Statistics for the Transition of Energy and Transport, which just has been granted funding this May for the first year period. And also noteworthy is the very successful activities in transfer, public outreach, and industrial collaboration with industry. And the strong cooperation of these three universities also manifested by the fact that they join forces also in the local organizing committee. Thank you for that. I had the opportunity to browse through the program, and this Congress addresses both advances in the theoretical foundations of the mathematical statistics and probability theory, as well as applications to a number of highly relevant questions and problems. In the coming 5 years, no, not 5 years, yeah, well, probably in the coming 5 years, but in particular in the coming 5 days, you start for the coming 5 years, possibly a very broad spectrum, an enormously broad spectrum, as I guess, of topics are obviously addressed. They're ranging from statistics and probabilities methods in data science and machine learning, which is obviously kind of also one of the focus topics here at that Congress, and which seems to becoming also a new and interesting topic in your community. Well, from that to extreme value analysis, for example, which can be used to calculate in advance the likelihood of very rare and extreme events such as droughts and floods and heavy rainfall. And this question, how much more likely, for example, such events are now, considering the climate change, is a pressing issue relevant for politics, for society, all over the world. It just highlights the significant relevance of the topics which are being here, and it's just one of the many examples which are addressed here in this Congress. Actually, being in my real life, Peter Eichelsbacher has addressed it, professor for structural analysis, I myself have a close affinity to probabilistic uncertainty modeling, as the safe design of our structure requires suitable methods for predicting very low probabilities of 10 to the power of -6 in that range, considering the heterogeneity of the materials. Just consider fiber-reinforced concrete. Never know exactly the orientation of the fibers. Or consider, for example, the uncertainty connected with the geology in tunneling engineering, or the stochastic processes governing the wind loading in wind turbines. Hence, from that background, I cannot emphasize more how important the advances in the fundamental research in stochastic and probability theory is to solve many challenging problems in engineering, but far beyond for our society. Having said that, I wish you all a successful conference, many fruitful discussions of the latest developments in mathematical statistics, probabilistics, and exchanges of novel and exciting ideas. I hope that you enjoy your stay in Bochum, and that you may have many joyful and memorable moments beyond the lectures and presentations here at the university. Make use of the wonderful summer weather we have and the organizing committee has organized for you. And explore, for example, the botanical garden, which is just a couple of minutes walking from here. And the adjacent original Chinese garden donated from the Tunji University, which is really worthwhile to visit. Or have a look in the unique mining museum in the city, or just enjoy drinks and good food in the many restaurants and beer gardens in the city area called Bermuda Triangle. But be aware and be careful, don't get lost, as you have to be fit for the next day. Well, having said that, I wish you all a wonderful and exciting 5 days of really new and important insights in your field. Thank you very much.
Thank you very much, Günter Meschke. The next opening message will be given by the Dean of the Faculty of Mathematics, Gerd Laures, is working in topology. And let me say, he is my successor since last October. I'm very happy, after 8 years being the vice dean or the dean of the faculty, now to be back in research and teaching. It's my pleasure. Gerd, please.
Good morning, ladies and gentlemen, and welcome to the Bernoulli-ims World Congress. My name is Gerd Laures, and I have the honor here to welcome you all as the Dean of the Faculty of Mathematics. It is a pleasure to see such a distinguished gathering of more than 900 participants from around the globe here at the Ruhr University, Bochum. As Peter said, I'm a topologist, and I must say I'm really impressed of the pure scale of this conference. In my own field, it's completely unusual to have conferences of this magnitude. This gathering with 15 plenary talks, 600 contributed talks, and more than 100 poster sessions underscores the vibrant community that statistics and probability has cultivated. The Bernoulli World Congress, Bernoulli-ims World Congress, has previously taken places in remarkable cities like Istanbul, Seoul, Toronto, and now it's our privilege to host you here in Bochum, a city well known for its beautiful weather, beautiful beaches at the Ruhr, and more important, for its rich academic heritage. Probability and statistics have long taken a crucial role in our faculty of mathematics, unlike many other institutions where these disciplines form their own faculty, their own department. We here in Bochum believe in the mutual enrichment that comes from maintaining them under the big umbrella of mathematics. Both theoretical mathematics and practical applied statistics can benefit from each other's advancements and insights by this integration. A good example for this is topological data analysis, where new methods have been developed to analyze complex data sets, and it demonstrates the powerful confluence of abstract mathematics and practical applications, data science, statistics. Our faculty has been home to luminaries in the field. I like to mention Hans-Georg Kellerer, Peter Gensler, and Sergio Albeverio in the past. And today we continue this tradition of excellence with scholars like Axel Bücher, Harold Dehling, Holger Dette, Peter Eichelsbacher, Christoph Külske, and Christoph Taylor. And I like to thank them and also many others, especially people from our neighbor universities, Dortmund and Duisburg-Essen, for making this event here possible and for bringing it over to Bochum. I also like to thank the German National Science Foundation, DFG, for its continuous support of our faculty with GRCs and SFBs and SPPs, and especially for its support of this conference. This conference not only celebrates the remarkable progress in probability and statistics, but also sets the stage for future breakthroughs that will shape our understanding of these fields. Once again, welcome to Bochum. I wish you all a productive and inspiring conference. Thank you.
Thank you very much, Gerd Laures. There is a very active section for stochastics of the German National Foundation for Mathematics, which is the German Mathematical Society. Claudia Kirch is the spokesperson of the Stochastic section. Claudia is working in mathematical statistics and applications at the University of Magdeburg. Dear Claudia, many thanks for coming. Please.
Yeah, thank you very much. It's a pleasure to welcome all of you in Bochum. And as was already said, my name is Claudia Kirch from the University of Magdeburg. And I have the pleasure to welcome you as the chair of the Probability and Statistics Group of the German Mathematical Society. So in German, we use the word Fachgruppe Stochastik, as you can see here. I think stochastic is more or less a word that is being used a lot in German. I'm not so sure internationally. And basically, it's for probability theory and mathematical statistics, so exactly what this conference is all about. Let me shortly introduce the group. So last year, we had the pleasure of celebrating our 30th anniversary. And the group was founded very much with the interest of promoting the probability and statistics in Germany in mind. To this day, we focus on providing a platform for young scientists and also fostering young scientists. So one example of how we do this is a biennial prize for the best PhD thesis. Actually, as of now, we have switched to having two prizes, one for the best PhD thesis in probability theory and one for the best PhD thesis in mathematical statistics within the last 2 years. The prize is always awarded at the German Open Conference on Probability and Statistics, which is an international conference organized by us. The next one will take place next March in Dresden in Germany. So if you like it here, you're very welcome to also join us there. As a Germany-based society, we are clearly much smaller than the Bernoulli Society or the IMS organizing this event. And this is one of the many reasons why I'm really happy that the 11th World Congress in Probability and Statistics is hosted here in Germany. And I think this is only possible because of all the people who helped making this event happen here. So I would like to take the chance and thank everybody who helped with this. In particular, of course, the Bernoulli Society and the IMS as the organizing organizations, but also the Ruhr University for hosting us, and of course, the local organizing committee, who put a lot of effort into this conference. At the forefront of the organizing committee, I would like to thank in particular Harold Dehling, who I know put a lot of personal effort into making this happen as well. Thank you very much. A conference of this scale provides an excellent chance for scientific networking, meeting old friends, making new friends, and getting to know new things. While I'm sure most of you are here for the scientific program and not just to cross off yet another destination on your bucket list, you might as well take the chance and explore the area a bit, which has a very long and important tradition in mining in Germany. Check out the conference website for some ideas. There's actually many suggestions there, and I'm sure you will be surprised of what you find. And with this, let's look forward to an exciting week with many interesting talks and stimulating discussions. Thank you.
Many thanks to Claudia Kirch. Now, as you all know, the Bernoulli Society for Mathematical Statistics and Probability was created in years 1973 until 75. There will be a celebratory session marking its 50th years of existence, which is tomorrow, starting at 5:45 in the late afternoon. Now it's my pleasure to welcome Victor Panaretos, Professor of Mathematical Statistics in Lausanne. He's the president of the Bernoulli Society. The World Conference is one of the major events under the guidance of the Bernoulli Society, beside many, many more activities for our community. Welcome to Victor Paneretos, but the two presidents like to come together, so let me switch to the next slide. The IMS is the Institute of Mathematical Statistics. It was formed in September 1935 at Ann Arbor in Michigan. The first president was Professor Rietz. The first president of the Bernoulli Society was Professor David Kendall. And I'm much delighted that Michael Kosorok from the University of North Carolina, Chapel Hill, has agreed to give an opening message. Thank you both. The floor is yours.
Thank you very much. Good morning. As president of the Bernoulli Society, I would like to also welcome you to the 11th World Congress in Probability and Statistics. I'm very pleased to see so many of you here today, literally in the opening ceremony. They're not usually so well attended necessarily. I will try to avoid repetition, but I can't omit expressing my deep gratitude to our colleagues for their wonderful service to our discipline. Thank you to all the organizers, local and scientific, for putting this together. I will not name them all, but Aurore, thank you. Kavita, thank you. Harold, thank you. Sometimes we take it for granted that things just work. But behind the scenes, there is tremendous volunteer work by our community, and we should not forget this, that our community works very much based on volunteering, essentially. So with over 900 participants, this promises to be one of the most well-attended World Congresses in history, certainly in the last 25 years. And I think it's actually possibly second only to the first Bernoulli World Congress. It was only Bernoulli, but it became Bernoulli-ims as of the second one, which took place in Tashkent, then USSR, in 1986. In fact, it has been nearly 40 years since that event, so in many ways this is a landmark Congress. Many things have changed since then, others a bit less so. There are some challenges that at times seemed distant relics from the past that seem to be re-emerging on the horizon. So I think the unity that the World Congresses represent, both scientific and otherwise, remains very relevant today. One thing is for sure, I think we can all agree today that the World Congresses have become the premier event in our disciplines. There is another landmark occasion already mentioned. Here in Bochum, the Bernoulli Society celebrates its Golden Jubilee. So 50 years since its founding by some of our discipline's leading figures. Please join us tomorrow evening for the special event commemorating this occasion, and also make sure to visit the Bernoulli booth near the entrance, where you can collect various commemorative memorabilia. I look forward to the rich and exciting program and wish you all a very fruitful and enjoyable Congress. Thank you.
Mostly we wanted to do this together because we had almost identical things to say. And so I'm not going to repeat everything, but just say, yes, I agree entirely with what Victor said. This is a wonderful opportunity, really to welcome all of you to this wonderful World Congress. I'm extremely excited about it. There are many, many wonderful events to look forward to, and I invite you to attend as many as you can. I think it's going to be a very rich experience. I also look forward to getting to know many more of you than I currently know. And the personal aspect of this is just making connections with people is extremely valuable. I would like to thank everyone that has helped to make this possible. Victor listed them. There are many of them, but I just can't overemphasize how tremendously wonderful everyone has done in planning this. I'm very excited about this what we're going to be doing here. And so thank you again, everyone. I also want to mention that the organizing committees have just done a wonderful job. I was very, also have to say as a musician, I just love the fact that we included music. William Byrd was an amazing composer, and this organ is a wonderful instrument. And for me, I don't see a huge difference between music and mathematical thinking. I probably should see a bigger difference, I just don't. And so I really like the added dimension that music provided. And with that, we just want you all to enjoy this conference, and I so much look forward to it. Thank you.
Thank you. So maybe we should hurry up a little, but anyhow, more than 4 years ago, when Holger Detter and Herold Dehling asked the Bochum Stochastic Group whether we should apply to host the World Conference this year, my answer was not yes and not no. The reason was that I was at that time, as I mentioned before, the dean of the faculty. I have been the spokesperson of all the other deans. We have 21 faculties, and I am interested in research, and I'm father of 5 children, and so on and so on. But as it became clear that Herold Dehling will be the chair of the local committee, I switched to a yes. I like to thank all members of the local committee, but I would like to point out the unbelievable amount of work Herold had. He had arranged a wonderful meeting. We all owe him many thanks for taking on the extensive job and for the executing it he always does, calmly and with perfect results. Thanks a lot, Herold Dehling. Thanks a lot, Herold. Please.
Now there is a very fortunate coincidence of a number of things. Number one, I have just about 2 minutes left. Number two, most of what I had planned to say has already been said. What is not so fortunate is that now on the spot I have to select from the 20-minute speech that I had to prepare the 2 minutes that are really super important. So I could tell you, for example, that if you calculate the number of persons per million inhabitants, then the top runner here at this conference is, well, naturally Germany, but it is just barely beating the Netherlands. So the Dutch are here very well presented, and I'm extremely happy about that because I have my first permanent position at the University of Groningen, and this morning I actually chose to take the tie of the University of Groningen here. And so thanks to my Dutch friends, hartelijk welkom hier. Wat mooi dat we een beetje Nederlands met elkaar kunnen spreken. So I will just leave it with some very personal things. The number one, I always have the pleasure to introduce the person at a conference whom I have known longest. And the older I get, the more impressive this number is. Now, unfortunately, the 2 persons whom I've known longest will only come tonight or tomorrow, but I nevertheless want to mention them. It is Manfred Denker, my PhD advisor, whom I have known for 49 years, and Götz Kersting, or Götz, are you already around? No, Götz Kersting from the University of Frankfurt, whom I have also known for 49 years. Then I thought, how many people did I know already before the first World Congress? And then I can add another 2 to the list. Rick Bradley, I already saw yesterday. Rick, are you here? Oh. And Istvan Berkes. One of the aspects that I enjoyed very much in the preparations here was the personal exchange, not personal exchange, but yes, it's personal exchange, but via email with quite a number of people. And one of the people was a big surprise to me to get a message from, about 2 years ago, Klaus Quickeberg. And I had before, one time, received a message from Klaus Quickeberg, which is a very dear document to me, namely in the year 1982, 42 years ago, Professor Quickeberg, who was then the editor-in-chief of the Zeitschrift für Wahrscheinlichkeitstheorie und verwandte Gebiete, and because nobody could pronounce it, it was called ZW, so the pre-runner of what is nowadays probability theory and related fields, but the tradition of abbreviating it as PTRF has remained. And this letter by Professor Quickeberg in German, real letter, informed me that my PhD thesis had been accepted for publication in ZW. And Klaus Quickeberg was the chair of the scientific program committee of the first World Congress in Probability and Statistics in Tashkent. And he would have been here were it not that he had an accident a year ago, but he sent me a greeting word, and I want to read this to you. Greetings by Professor Quickeberg. You might wonder how old he is. He's 95 years old. Gentle ladies and gentlemen, the idea of a World Congress in Probability and Mathematical Statistics is due to Zerazdinov. He suggested it to me on the 26th of April 1966 when I visited the Institute of Mathematics of the Uzbek Academy of Sciences. Now you are in the 11th World Congress. I'm not among you because I had a little accident. Hence, I'm sending you in writing my best wishes for an interesting, profitable, and enjoyable meeting. The first World Congress took place in the year 1986. I have participated in it and in some of the congresses that followed. There has been steady progress in the quality of the contributions, but also in organizational matters. The Congress is now carried by the Bernoulli Society and the Institute of Mathematical Statistics. I'm particularly happy about it because I was the second president of the Bernoulli Society and I'm a fellow of the IMS. I regret, though, that the word mathematical was dropped from the name of the congresses. Although my own scientific interests have somewhat changed over the years, I studied the program of the present meeting in detail and I found an impressive number of interesting contributions. Hence, once again, I'm wishing you all an excellent Congress. So thank you very much, Klaus Quickeberg, if you're watching us at the moment. Thank you very much for this note. I could continue with a lot of thank you notes now. In the first place, I want to thank the colleagues on the local organizing committee and especially my colleague Peter Eichelsbacher, who did a tremendous amount of work and especially making sure that he was looking at the big picture of the conference when I was sometimes getting absorbed with the little details. And I want to thank the chairs of the scientific program committee. And you might have wondered what I brought here. So I brought something that you can only get in Bochum. And this is a gift that each of the plenary speakers will get from us. I thought for a long time, what could I give? I will not tell you what other ideas I had. This is knowledge. You can get knowledge from Bochum. Ruhr University Bochum is the only university in the world that produces its own perfume. And this perfume is actually created with the help of a colleague in the biology department who is a world-leading scholar in the physiology of smell. And so this perfume is supposed to enhance creative thinking, so knowledge from Bochum. And now I would like to ask Aurore de L'Aigle and Kavita Ramadan to come, because you will be the first recipients of knowledge. Thank you very much for reading So I will skip all the other words that I had, and now thank you very much. I wish you a fruitful conference.
So thanks to every speaker, to all the speakers of our morning session. We would like to have a photo just after a few more words. Please come into the front of our building. A politician might say, I declare open the World Conference, but I'm simply pleased to continue now with the scientific program of this Congress. Unfortunately, the first speaker, Professor Michaela van der Schaar, is ill. She decided to stay at home, but good news is that she will give her lecture via Zoom. So we will prepare this within the next 5 minutes, hopefully, to define the technical details, and the chair of our first plenary lecture will be the president of the Bernoulli Society, Victor Panaretos. Thanks a lot for this opening session. Thanks for listening.
Yes, I can. I'm going to try to share my screen as well. Oh, God.
Okay, good morning again. Before Mihaela shares the screen, let me welcome you to this year's Tukey Lecture. As a scientific grandson of John Tukey, I'm particularly happy to be introducing this year's Tukey Lecture, Professor Mihaela van der Schaar from the University of Cambridge. Mihaela is researching primarily machine learning for healthcare, but she has very broad interests, and looking back in time, she has worked in multimedia compression, wireless networking, multi-agent learning in engineering systems, among many other topics. Mihaela hails from the Netherlands. She studied through the undergrad and the PhD in Eindhoven, and then started her career at Philips Research as a research scientist and later a senior research staff member. She then moved to California, initially UC Davis as an assistant professor, and then UCLA, where she rose the ranks to professor of electrical and computer engineering. Then she jumped back over the pond to the United Kingdom, where she became Mann Professor in the Department of Engineering Sciences of the University of Oxford. And then finally she crossed the biggest of the divides, moving to the University of Cambridge, where she is John Humphrey Plummer Professor of Machine Learning, Artificial Intelligence, and Medicine. She has received a career award from the National Science Foundation. She's an elected fellow of the IEEE. She has been a Chancellor Professor at UCLA, and she has also won the Owen Prize in Preventative Medicine from the University of Cambridge in 2018. And today, Mihaela will be talking to us about a machine learner's journey in the footsteps of Tukey. Thank you, Mihaela. Over to you.
Thank you very much for your kind introduction and for the invitation to give this talk. Hopefully you can see my screen all right.
Looks good,
Can
yes.
you see?
Yes, looks very good.
Wonderful. Okay, so thank you again for the introduction, and I really wish that I would be in person today to deliver this talk. Unfortunately, I'm ill, so I cannot, but I'm absolutely excited and delighted to give a presentation in which I would like to make a personal appeal to you all in the audience to consider John Tukey's work and words of wisdom and use it to inspire you like it has inspired my work. And today I'm going to plan to tell you about how John Tukey has inspired my own footsteps in machine learning and beyond. I'm going to start by discussing how John Tukey thought about choosing the right question and how he was very happy being a statistician playing in everyone's yard. And I'm going to tell you about my own work on reality-centric AI. Then I'm going to take you back in time to my time in Philips when the fast Fourier transform enabled me as a beginning junior scientist trying to make a breakthrough in internet and wireless video compression. The majority of the talk is going to discuss how I am inspired by John Tukey's view on exploratory data analysis to explore a dimension that has been very underexplored in machine learning, but more generally in statistics and data science, time. Then I'm going to just say a few words about John Tukey's interest in data analysis, especially in cases that the data is messy and spotty. And I'm going to talk about the current paradigm shift from model-based AI to data-centric AI. Okay, so let us begin. I'd like to start with this quote from John Tukey, which many of you may know: far better an approximate answer to the right question, which is often vague, than an exact answer to the wrong question, which can always be made precise. So let me take you to my own field, AI and machine learning. In the past few years, we have seen significant advances in AI with the emergence of ChatGPT, more generally generative AI, advances in robotics, advances in a variety of applications enabled by AI. So we have seen enormous leaps in AI. And yet, have we seen a transformation of healthcare systems? For instance, AI has not fixed NHS in the UK or enabled us to control the exorbitant costs of healthcare in US. Have we alleviated traffic? I used to be in many traffic jams while waiting to go from my home to my university in Los Angeles. Have we solved the energy crisis? Or are we able really to prevent a climate catastrophe? And what about the next financial crisis? Or for that matter, have we transformed education? I'm going to invite all of you who are students or educators to consider a Roman schoolmaster walking in 2024 in your classroom. My guess is that they will recognize immediately what is going on. Not that much has changed in 2000 years. And I'm really going to say that I believe that we are not just a few breakthroughs away in solving these real world challenges. And part of it is machine learning at a cutting edge. As you can see in the top conferences in AI and machine learning to which I participate, is unfortunately very focused on toy benchmarks and petri dish problems. And what I believe we need is a new paradigm to orient it towards the complexity of the real world. So note that I'm not saying that machine learning and AI cannot solve these challenges or cannot play an important role in real world domains. Rather, what I am trying to say is that we need a fundamentally different paradigm to think about this and orient AI towards the complexities of the real world, thereby following in the footsteps and the words of John Taki. So what I have put forward 1.5 years ago is a manifesto which I call the Case for Reality-Centric AI. You can find it prominently displayed on our website. And what I'm trying to do in this manifesto is to compel AI and machine learning researchers and more broadly data scientists to really consider addressing real-world problems, even though they are messy and complex. And I'm outlining in that an 8-point agenda. And the key points really are to build AI that can solve real-world problems, even though these real-world problems may be complex and we may not have a direct solution immediately, but rather an approximate solution. At the same time, by considering these complexities as well as the need to abstract these complex, intricate real-world problems and formalize them into a way in which we can address it using machine learning and AI, we are going to make an important step. I'm also advocating for building an AI that is empowering for humans and remains in the control of humans. So again, it is better to answer the right question and try to solve real world problems, even if often we are going to do that one step at a time, than trying to solve petri dish problems like often currently we are doing in the top AI conferences. And indeed, in my own lab over the past 20 plus years, we have tried to engage with a variety of topics. As Peter has mentioned, I started by looking at how can we transmit video over the internet and wireless networks at a time at which it was not possible. And then I moved to solve problems in smart cities, transportation, finance, energy grids. And in my recent period, I've been very interested in building AI for medicine and healthcare and education. And again, one thing that resonates with me is what John Tuckey said about The best thing about being a statistician is that you get to play in everyone's backyard. And because I'm not a statistician, neither I'm actually a computer scientist, I'm an engineer by training. I think the best thing about being an engineer or a data scientist or a computer scientist working in machine learning is that you get to solve real world problems in a variety of areas, and you can really move across these different fields because you are stimulated by the real world problems it poses. And I believe that medicine and healthcare, as well as education, are not only very important problems for humanity, but also very challenging ones. So if I am to paraphrase John Taki, I'd like to say that far better to focus on reality-centric AI, even if solutions are imperfect, than to chase perfection on toy benchmarks, which may be irrelevant. And this is why I propose this reality-centric agenda. Let me now say just a few words about fast Fourier transform. And let me say that I've been very fortunate early in my career to join Philips Research when I was quite young. And actually, I've done my entire PhD while working full-time for Philips Research. And I've had the opportunity to work on a variety of real-world problems, really that enabled transmission over the internet and wireless networks at a time that it was not possible. And Philips was tremendously visionary, allowing a relatively young kid to represent them in standardization and work at this pioneering technology. But what I'd like to tell you is my first project at Philips, age 24, where we were trying to build our first camera to do video conferencing over the internet. And I tried actually to find online the USB camera that I worked on, and I cannot find the earliest generation that we built. I found a later generation, but this camera that Philips built in 1996, 1997 was actually a very first design of a USB camera enabling us to do video conferencing. Yes, I am that old. And I needed to use DALI on the right-hand side to kind of envision the setup because I do not have a picture of that setup. But what was interesting was that we were trying to capture videos in real time and transmit them over a network. And the challenge was manifold because this camera was done in hardware and our algorithm for video compression needed to work in real time and capture and compress information in real time. Yet, in the software, we needed to decompress this information as well as compress it into a much more powerful and lower bitrate format to transmit over networks. So we had the hardware-software co-design problem, which involved stringent bandwidth requirements because we needed to pass through a USB cord, which was requiring its own compression, and then over the internet requiring yet another compression. We need to do that in real time and at a very, very low cost. And we did that. I built this algorithm. I'm very proud, actually, that I built this algorithm in my early to mid-20s. And fast Fourier transform played a very important role in that. And we needed to play with different instantiations of fast Fourier transform because in hardware, we needed one type of implementation, and then in software to enable real-time processing, a very different one. So fast Fourier transform in different incarnation, back to John Taki. Let me now move to exploratory data analysis, which we know was very much invented and developed by John Taki. And I'm going to tell you about my own fascination with it, which involves time, which is often an unexplored dimension. But in medicine and many other areas like finance and so on, time is really a very, very important dimension that is often not well explored. So often we are interested in discovering from data and exploring data to discover powerful models. And for that, we need to go beyond what currently we do in machine learning and AI. We need to go beyond prediction. We need to understand complex variables, relationships of this over time. We need to experiment judiciously and act in a way in which we understand. Over the eras, human scientists, human experts have been the ones that have discovered such governing equations, from the physics to the physiological to the psychological. And such brilliant domain scientists bringing their knowledge and intuition and brilliant minds, have teased out equations from the underlying data and formed new hypotheses which empower us, humanity. But time is very complex, and often we do not have such big discoveries that empower us to understand how dynamical systems, complex dynamical systems that are really the real world, from medicine all the way to finance, to climate, to smart cities, really are lacking. So what I'm going to propose to you today is that we need to do exploratory data analysis to unravel governing equations. And by governing equations, I mean compact and closed form equations, which are concise, generalizable, amenable to further analysis, transparent, and allow the human to remain in control. What do I mean? I'm going to show to you a few here in terms of physics, but today I'm going to talk about time and I'm going to talk about medicine. I'm also going to try to convince you in this talk that we need to go beyond association over time and beyond causality over time to what I'm going to call the ultimate ladder, which is discovering governing equations of dynamical systems and how they evolve over time. So unlike in association where maybe a specific chemotherapy drug is associated with a certain side effect over time, such as liver dysfunction, and unlike causality, where I may have a graph structure that may uncover the role of interventions and treatments, for instance, this specific chemotherapy drug may have this particular impact on women, which may cause this liver dysfunction over time. I'm going to talk about discovering governing equations, for instance, quantitative analysis in which we discover the drug effect over a tumor, for a tumor growth over time. Okay, so let us begin with the very beginning, risk equations. And often currently we rely on statistical models. For instance, you see here the NHS predict breast cancer equations that inform us about cross-sectional data and how can we make risk prediction for patients. What I'm going to try to move this risk prediction is towards time, because medicine is actually a time endeavor. And currently in time, we do not have transparent models. We do have explanations of time series models, black box models, in the form of post hoc explanations, for instance, feature importance over time or example importance over time. And this work actually has happened in our lab. We have been the first group really to try to look at post hoc explanations. But in medicine and many other domains, this is not enough. We really need transparent models. They are essential for understanding, for discovery, for early diagnosis, and for human empowerment. And for that, currently we have only static predictions, linear regression, decision trees, generalized additive models, or some methods that we have built in our own lab, trying to go beyond such methods, such as tree of predictors and shares. Unfortunately, all of those are powerful models, transparent models, but static. What about time? In time, we want to predict an entire trajectory. We want to forecast transparently in the time series domain. So why do we need transparency? For instance, we want to forecast the tumor volume trajectory from a patient's baseline covariates and drug dose. And standard interpretability techniques such as feature importance or example-based methods, which we often see in machine learning, may be able to answer questions such as how important is a specific covariate, for instance, gender, for the prediction, or how similar is the instance for other instances in the data set. But to understand and discover, we need to go one step beyond. We need to be able to answer questions such as, what if? What would happen to the model's prediction if a specific covariate changes? Or how should the covariates be modified to get a different prediction? Or what range of drug dose values will keep the prediction for this patient the same? So in order to be able to answer what if, what to be that, what to still be this, we need to understand the change in the trajectory. And this is more challenging, and this is a challenging issue in time series. We have very recently able to conquer for the first time this and build what I believe to be the world's first time series interpretable model, which enable interpretable predictions, but also effective visualization, and we call this time view. And this is work together with my brilliant student, Christophe, who is a mathematician by training, and Tennyson, who is an engineer like me. And in time view, what we are doing is we are having time series data, including both static variables as well as time series variables. And we are trying to build powerful predictive models as well as visualization. And we realized that using motifs, which enables us to describe increasing trajectories, decreasing trajectories, enable us to describe parts of a time series trends. So you see here, for instance, increasing and strictly convex, straight line, for instance, with a zero slope, as well as the points, the coordinates, where we can map these properties of a trend. And what we are going to have is we are going to have dynamic motifs which encode this information about the trajectories' first and second derivatives. You see here a few dynamic motifs which we have used in our work. And what we are doing is, in this work, we are going to determine the points between motifs, which we are going to call transition points, and the coordinates at which this is happening are going to be mapped to the properties of a trend. And these transition points between the motifs are going to correspond to the local maxima, local minima, as well as inflection points. And these are the exact properties used in a standard mathematical exercise, for instance, of function sketching, whose goal is to precisely understand the function trajectory. But what we are going to do here, we are going to learn this from data, and we are going to learn such motifs as well as transition points from data. We are also going to formalize the notion of a trend by defining the composition of a trajectory. Then, to realize transparency through these dynamical motifs, we need to first understand the relationship between the feature vectors x and the composition of predicted trajectories. Then we need to understand the relationship between these feature vectors and the transition points of a given composition. And to be able to fulfill this condition, we need to really find a space of trajectory that satisfies the following criteria. First, we need to have a set of dynamic motifs which is compatible with the class of predicted trajectories. And number two, we need to, for every such predicted trajectory, we need to calculate its composition. And a way to do that before training is to use cubic splines, which are a very wonderful class of functions that satisfies both these desiderata that I mentioned before. And in our work, we are able to prove that dynamic motifs of the type that I described before are indeed compatible with cubic spline. And moreover, it is easy to calculate the dynamic composition of a cubic spline as a piecewise function consisting of a set of cubic polynomials connected at knots. And then we are able to show that each spline is described by a latent vector, which we need really to learn from data and forecast from data. And finally, at runtime, we need to be able to match this function vector x to latent vector c, and we are going to learn that using an encoder which is able to learn such a mapping using a neural network. So then what we have actually at runtime, we are able to make forecasts, we are able to predict the different trends as well as properties of the trajectory into the future. For instance, you see here how we can predict from data the tumor volume and how it changes as a function of the many variables. And we have a very beautiful visualization tool that is able to do that. So again, going back to John Taki, the greatest value of a picture, this time a picture over time, is when it forces you to notice what we never expected to see. So by using time view, we are able to see this forecast into the future and how they are changing given these different trends. Let me now say a few words about more complex situation. In particular, I would like to tell you how we can learn from data transparent ordinal differential equations. Because in medicine, again, everything it's a dynamical system. And this is a much harder problem. So, of course, we have often in medicine dynamical systems which are modeled using differential equations that describe how the state of a system changes over time. And for that, we often observe actually only time derivatives. So the challenge becomes, how can we learn the underlying ODE from such data? So the challenge is to use data sets and machine learning to learn ODEs, thereby discovering structural knowledge. So we have trajectories that are evolving over time, and we want to learn from these trajectories the underlying system of ODEs that have generated these trajectories. And we want to do that in a transparent way. This is challenging because the time derivative is not observed. We only observe the states over time, and conventional symbolic regression methods are not applicable in this setting. It is difficult to estimate the time derivative, so hence the states are observed often sporadically with noise. There may be a chaotic system. So estimation of such time derivatives are usually very prone to error and failure. Also, it is difficult to directly solve the initial value problem of ODEs. And this is really challenging to infer the initial condition from data. It's also sensitive to noise, to limited data, and is also computational challenging. So what do we do in a paper of a few years back that we call Decode? We are circumventing this idea of measuring and estimating ODEs. How are we going to do that? We are doing that based on the variational formulation of ODEs, which are able to characterize an ODE without referring to the derivative. So to understand how and why Decode works, we need to just very briefly familiarize ourselves with the variational formulation of ODEs, which enables us to do this characterization of ODEs without derivatives. So what is important to note is that if we are to use this variational formulation of ODEs, expressions do not contain the derivative of x. They do involve the derivative of g, but g is something that we construct, which for an engineer like me or for a constructional statistician like Turkey is wonderful because we can choose g. In such a way that the derivative is easy to compute and calculating the whole functional is no longer challenging. So the variational formulation of ODE now states that the differential equation holds if and only if the corresponding functionals are equal to 0. And in addition to providing a theoretical justification of our algorithm, this theorem, which we have proven in our paper, also guides us in the choice of choosing this testing function g. So we need to choose functions that form a Hilbert basis for the L2 space that are continuously differentiable and vanishing at endpoints. And one particular choice is the Fourier sign basis. So again, you can consider the situation that you are going to use potentially a fast Fourier transform, all the way going back to Tukey to solve this particular problem. In effect, actually, what we do is in our decode algorithm, we are pre-processing the data, and then we are evaluating it on all estimated trajectories from the first step and all the pre-specified testing trajectories. And this enables us to do the actual optimization very simply, and we don't need to compute anymore the derivative, but rather in this case, we are able to use these functionals, these testing functions. It could be fast sign transforms, and we are able in this way to do very simply symbolic regression. And note that in this way, we estimate the trajectories, not the derivatives, making our work very easy. In a set of experiments, first we were trying to see, can we really discover from data things we do know? So what we do is we generate very noisy data that's irregularly sampled. We have limited number of samples, and we want to see if we can indeed unravel from such complex data these dynamical systems correctly. And you see that indeed decode is able to do that, while two-step symbolic regression, which is the only other method that is able to do that transparently, is not able to. And you see that in a particular scenario highlighted here, we do that for many different types of experiments and dynamical systems, but here is highlighted for asymmetric growth with saturation, complex models, generalized logistic models, because they are often prevalent in medicine. We can also do that for chaotic and non-periodic systems, and this is even more exciting because here not only methods such as symbolic regression fail, but if you are going to try to do this, to solve this problem using non-transparent models such as neural ODs, which are one very famous machine learning method currently used, you will see that even they are failing because of the challenges associated with solving the inverse value problem. However, decode is able to solve that elegantly. We also have used decode to try to discover something we do not know. And you see here an example where we use 8 clinical trials on cancer patients, where we have tried to unravel the effects on chemotherapy on tumor volume and try to discover underlying governing equations for such patients. And what you see is that the trajectories are much better represented than what symbolic regression can do. In particular, the relapse that we see in a set of quite a large set of patients is correctly unraveled. I'll say a few more words about that a little bit later, and the relationship to causality. But before I do that, I want to say just a few words about partial differential equations. And can we discover partial differential equations from data? And this is an even harder problem. And there, the variational formulation cannot be directly applied, and it is even more difficult to search. And as I mentioned, this variational trick may not work. So what we do in a recent paper called Decipher, we are able to discover closed form partial differential equations by defining a new class of PDEs which are accepting variational formulation. We show that this class is actually a very large class, and for this class we are able to discover PDEs from data. The reason this is exciting, not only mathematically, but also practically, is that while we decode, because we are able to discover ODs, we can discover tumor growth models, pharmacological models, epidemiological models. However, with Decipher, we can go one step further and we can discover spatiotemporal models, including spatiotemporal tumor growth over time and how cells are changing over time. We are able to discover populational models as well as age structure epidemiological models, thereby being able to go one step further to empower clinicians and medical scientists. I said that with these methods, we can climb the discovery ladder. And I promise to you that I'm going to make a relationship to causality, and I'm going to explain why I believe that this represents one step further. If you think of the world of causality, often the focus is on graphs and relationships between variables. But this is not enough. It's not enough to know that this particular variable has caused this particular outcome. We really need to know how, and we really need to know entire structural equations and how they evolve over time. So we need really to discover governing equations and how they respond to interventions over time. This represents, in my opinion, the true step on the discovery ladder. This will enable us to answer questions such as how to treat, when to give treatment, when to stop treatment, and enable us to understand the trajectories over time, as well as understand the counterfactuals that may result from different decisions over time. This is, of course, a very complex causal problem because it involves longitudinal data. And because of that, we are having time-dependent confounders, which are going to bias the treatment assignment in the observational data sets from which we learn. What type of observational data sets I have in mind? Electronic health records, or any type of observational data where we have decision makers making decisions over time. And these type-dependent confounders are nothing else than patient covariates, which are affected by the past treatments, which then influence the treatments and outcomes over time. So you see here in this particular diagram, just a two-step setting where we show how the bias from time-dependent confounder is affecting over time these variables as well as outcomes. And this is challenging in causality and a tricky problem to solve. It's a complex causal effect inference problem. Over the last 7+ years in our lab, we did a lot of work on trying to solve such causal effect inference problems. Often we also call them individualized treatment effect problems because we are very interested in personalized and precision medicine for the individual. Initially, we focused a lot on static information and do causal effect inference in static data, but then very fast, because we are working with clinicians, we realized that we really need to focus on this problem over time. This is a long journey for us. If you want to see a lot of the work that we have done, I refer you to the previous slide, which contains a link to our website. But more recently, together with collaborators, we are really able to bring that all the way to practice of medicine and also to pharmacology, where we made really, together with pharmacologists, quite a lot of progress in being able to do precision dosing, as well as determining really how to best treat patients over time. Let me tell you a little bit about this and the bridge to what I described before. So conventionally, this problem has been for the first time addressed in seminal work by Robbins, Hernan, and Brumbach, where they have looked at average treatment effects and trying to handle time-dependent confounding using marginal structural models by doing inverse probability of treatment weighting. Almost 2 decades later, we embrace this work and try to build machine learning models, recurrent marginal structural models that are able to personalize effects of treatments. Then, in a series of work, we have looked at counterfactual recurrent neural networks that depart from looking at inverse probability of treatment weighting, but rather use more powerful methods and ideas from machine learning to deal with these biases by using domain adversarial training, and then even more recently being able to deal with sporadic, irregular observations, as well as more complex trajectories by doing neurally controlled differential equations for treatment effects. But all of these are neural networks, and there is a problem associated with estimating treatment effects from data using neural networks, because they are not actionable really for clinicians. They are not interpretable. They cannot easily and naturally deal with irregular sampling and continuous trajectories. Also, they have a large hypothesis space, and often they result in low performance. So what we did is we decided to use transparent structural equations to learn from data transparent structural equations, which is a much higher bar. But if we are able to do that, this has advantages as opposed to the deep neural networks, because they are interpretable, they can learn from irregular and continuous sample data, they have a smaller hypothesis space, and often lead to a better performance, because as we constrain the hypothesis space, we achieve better performance in settings that satisfy our requirements. But there were many challenges. So this has been a dream for us for many years, but for quite some time we were not able to conquer the many challenges associated with this. Neural networks, as well as machine structural models, have a different way to learn from data. The problem descriptions were different. And if it is to use some of the methods that I described previously, such as decode, for instance, static features are not considered. We only focus on time series evolution. Also, the ODE discovery methods find only a single equation for an entire data set, and we don't want that. We don't want a population level model. We want an individualized model, so we need personalized ODEs. And finally, we want to have treatments which are not only continuous, we also want to deal with binary treatments, categorical treatments, as well as multiple simultaneous treatments. Finally, this year, we were able to do all that in a work that we call OD Discovery for Longitudinal Heterogeneous Treatment Effects. And what we do here is, as I mentioned before, OD discovery methods require a set of observed trajectories, and the treatment effects involve a data set of covariates, treatments, and outcomes. And what our contribution has been here is to create a usable framework that allows us to translate any OD discovery method into a treatment effect problem formulation. And while other treatment effect inference methods have used ideas from the ODE discovery literature, none of them has focused on ODE discovery. So, for instance, our own work has used opaque neural ODEs, neurally controlled ODEs, but in this paper, we are the first to explain the differences between the transparent ODE discovery and make the link to the treatment effect, causal effect literature, and reconcile the differences. We also propose a first method called Insight as an illustrative method to do personalized and transparent discovery. So what is really the challenge? Electronic health records data, or for that matter, trajectories of longitudinal treatment effects data, so data sets where we have interventions and biased sample, are the data sets from which we need to learn personalized treatment effects, causal effect inference in a personalized way. What the literature on standard treatment effects does, it learns a representation, so that's the middle panel, learns a representation of the data and uses this representation for inference. What we do instead is we learn a personalized and transparent OD for each specific patient in the data set. This is enabling us to learn causal effect inference. And also in this work, we are able to reconciliate the discrepancies between this work of causal effect inference as it was before and the work of OD discovery, which has, as I mentioned, different assumptions, discrete, not continuous treatment plans, and deals with the variability between patients. How do we do that? We do this reconciliation in 3 steps. First, we are transforming an ODE discovery method into a treatment effect method that results in a new set of identification assumptions. And what we show is that this is not a limitation, quite the opposite. This extends the typical causal effect, treatment effect literature identification assumption and is able to relax many of these assumptions. And by accepting ODE discovery assumptions, we are in effect relaxing a lot of stringent assumptions that have been made in causality over the years. Second, we are incorporating treatment plans as dynamical systems, and we are able now to deal with binary, categorical, multiple, and continuous treatments. And then in the classical ODE discovery setting, we usually have one kind of between subject variability corresponding to a noisy measurement. And this is what we call residual unexplained variability, or RUV. However, there are a few other types of variability that need to be accounted for if it is to do treatment effect inference. And we are able to reconcile this and unify these two worlds in our work, thereby being able to connect the world of personalized ODEs with the world of causal effect inference. So this enables us to really progress from methods such as time view all the way to enabling us to do transparent discovery of structural equations under intervention. And this is, of course, just the very beginning of what I hope to be a very big and powerful agenda to empower scientists to discover using artificial intelligence, machine learning, and data science underlying dynamical systems. Finally, just 2 words about another aspect of exploratory data analysis and gathering data as Taki inspired us. So on the website of the Institute of Mathematical Statistics, there is a very beautiful article which was written by David Hunt. And what he is saying in this article, which I recommend to all of you to read, is he's going back to The Future of Data Analysis by John Taki, and he's highlighting the interest that Taki has on data. And not high quality data, but realistic real world data, which is spotty data. Data that has all sorts of heterogeneity in precision, incomplete data, messy data, and data that has problems on selection, not data that just falls from the sky. So often what you will see in AI and data science, people want to have the perfect data set, and this needs to be super clean. But this is not the real world. The real world is like Taki highlights. It's a messy, real world, spotty, heterogeneous data. And this is actually very inspiring because currently we are undergoing a shift from model-based AI to data-centric AI, which is AI that focuses not in building yet another analytic model, but rather using AI and machine learning and its power to improve the quality of the data, to deal with small sample regime data, heterogeneous data, spotty data, as well as to how to acquire judicious data. And what you see here is a tutorial which I gave recently at NeurIPS, which is one of our machine learning conferences, together with one of my PhD students, Nabil, and my collaborator, Isabel, where we have focused on new advances on data-centric AI to enable reliable and responsible machine learning. So if you are interested, in view of time, I cannot tell you much about that, but you can see the tutorial on our website describing new advances in AI from a data-centric perspective. With this, I'd like to leave you with my own response, if you like, inspired by Taki. Far better to focus on reality-centric AI, even if solutions are imperfect, than to chase, like we currently do in cutting-edge machine learning conferences, perfection on toy benchmarks, which may be irrelevant. Thank you very much.
Now, we started a bit late, so I'd like to allow 5 minutes for questions. Mihaela cannot hear the audience. If you have easy access, you can walk down here and ask your question, or you can ask at the microphone and I will transfer to Mihaela. Maybe I can begin with a question. A lot of what you said resonates with me. It's very close to some of my primary sort of interests, which have to do with functional data. Does your work make fruitful contact with some of the methods on principal differential analysis or estimation of ODEs? There are some old papers by Ramsey and Hooker and so on. Is this connection being made?
Not enough, Peter. So actually, what is unbelievably inspiring, I think, in Taki's way of thinking is that I think he transcended boundaries between computer science, engineering, statistics, pure math. And I think we don't do enough of that. Often in the field of machine learning, we are, let's say, we keep a closed door. And I think that a lot more needs to change from that. So often we are unaware of ideas that come from functional analysis, that come from statistics. So in my own lab, I'm an engineer by training. It is natural to me to bring the world of signal processing, the work of frequency analysis, and often I have brought this world to the machine learners, bringing a way of thinking in the frequency domain, which is very new and different for the machine learners. So we have done that easily. Bringing powerful ideas from mathematics to machine learning is challenging for us. So I want to say to everyone in the audience, if you are interested in these problems and you are keen to collaborate with us, we are very, very keen to collaborate with you. We want to learn from you and together make a difference to empower machine learning and AI. We have been quite inspired by powerful statisticians. I mentioned here Robbins and Hernan. There are two statisticians that have empowered us very much. But the work of functional analysis in particular, I think, could be unbelievably powerful for AI and for time series analysis. And we need to learn much more. So Peter, please reach out and please encourage colleagues who are there to reach out to us and try to really make this bridge such that we can use on one hand powerful machine learning methods, but combine them and inspire them with fundamental work that already exists for decades and possibly centuries in mathematics.
Thank you, Mihaela.
Thanks for the great talk. I have a kind of general question about, it's more like a career type of question. I think a lot of like young researchers, also including me, are interested in addressing real-world problems. But at the same time, it's really hard to find these problems because most of the time, like people with real problems only approaches like people who have like well-resourced, who are well-resourced or like kind of already recognized in the field. So I was just wondering like what kind of advice would you give to like early career researchers who want to address like real-world problems?
Were you able to hear the
I
question?
apologize, I did not hear, I cannot hear. I'm sorry.
So I will try to summarize, maybe without the introduction. Is there some advice you can offer to early career scientists entering this field from the side of statistics?
Yes, I would say first, big welcome. I think you can make a tremendous impact in machine learning. As a matter of fact, my own lab, even though I'm an engineer by training, working in cutting-edge AI, machine learning, I have in my group a large number of young statisticians who have studied statistics in their undergraduate or graduate studies, and they made this transition to machine learning. The reason I think that you can make a tremendous impact is first, the way in which we analyze and think about data in machine learning is often imperfect and incomplete, and your rigorous knowledge of statistics enable you to think very differently about data. So this field of data-centric AI, which I highlighted, is a field where I believe you can make tremendous contributions. Another important field that I write a lot about, and it's an inconvenient topic for machine learners, and not often talked about, is that many AI and machine learning models fail when used in the real world. And the reason is we do not, when we take them to different types of data, with data which has shifts and drifts and different values of noise or missing data, often these methods are not sufficiently tested. So the way in which AI is currently trained and tested is not robust enough. And again, your statistical training, I think, can be transformational in making machine learning and AI more robust and more reality-centric. So please join. There are numerous problems at the fundamental level to make AI and machine learning more useful and more robust, either by looking at data or by looking at model robustness. And finally, the field of causality, I think, needs new sets of thinking, new sets of engaging with the key questions. And we are stuck in just, let's say, two current ways of thinking, which are powerful but not sufficient, either the work of Neyman and Rubin or the work of Judea Pearl. They are very powerful, but they are putting us to think only in one particular way of thinking. And as I've shown in my last work, I believe that there are new ways of thinking that may come from functional analysis, they may come from a new and fresh look at looking at data, observational data under intervention. And I think somebody with a statistical or pure math background has a lot to add to this agenda. My own student, Christophe, whose work I highlighted here, is a pure mathematician who I coerced into becoming a machine learner.
Thank you, Mihaela. Maybe one last quick question. Yes?
We hear each other. Thank you. Thank you for interesting lecture. My question relates to the mathematical part of what you have said. I think your analysis is based, if I hear correctly, the fast Fourier transform on L2 and Hilbert spaces. This relates to Victor's question. Is this possible to extend to even LP, where P is higher than 2, or to Banach spaces, to higher dimensional and different functional spaces? What to do with the fast Fourier transform, and what to do with learning ODEs, PDEs on other functional spaces? Thanks.
Okay. So I'll try to summarize. So your methods were based on the fast Fourier transform, operating on real valued functions, or operating in elements of L2. The question is what happens in LP spaces for different P, in Banach spaces, or even in infinite dimensional spaces, which combines with partial differential equations.
So this is an interesting and complex question. So for instance, for the, let me just say that right now, the decode, the method that I highlighted, I think is just the beginning of an agenda. In our work, we look very much at relatively low dimensional spaces. So we learn from relatively low dimensional data. We don't have currently a way to really make this method scale for very high dimensional data. So if you have ideas that can help us there, please do. Let me say that in the code, what we do is we are using these methods just to enable us to do, let's say, denoising and estimation. But I think that, yeah, I think a lot more needs to happen. I don't really know how to scale it beyond L2, and right now we just use relatively simple discrete Fourier transforms to do that. Whether better basis would lead to better solutions, especially in high dimensional spaces, please teach me.
And on this note, thank you very much again, Mihaela.
Thanks a lot. I hope I make some friends that will join forces with us to try to bring this type of agenda further.
We're very sad you couldn't join us. If you were
I'm
here,
very sad as well.
I would be handing you a certificate for the Tukey lecture.
Thank you so much.
A box of knowledge.
I need to
which
come
you
one
asked
day.
for.
I hope I get better and to come one day to take it in person and also listen to the beautiful organ that you have on the background. Thank you very much,
Thank you very
everyone.
much. Thank you very much.
Thank you for this opportunity.
Also, thank you to the audience, and I believe now it's time for a coffee break. Don't forget to go by the Bernoulli booth if you get a chance. Thank you.
Good afternoon to everybody. My name is Eva Löcherbach. I'm very honored to introduce the speaker of the DUP lecture of today, Pablo Ferrari. Pablo is professor at the University of Buenos Aires, and he's a member of the Bernoulli Society. Before, he was professor at USP in Sao Paulo and visiting professor at a lot of places like Rutgers, Paris, Rome, Santiago de Chile, Cambridge. He is also co-principal investigator of the Brazilian research center Neuromat. That's actually where I met him. His research interests are extremely broad, going from statistical mechanics, interacting particle systems, stochastic processes, to long memory processes and their perfect simulation. And he has also touched statistical inference problems on random graphs. Recently, he has been working on hydrodynamic limits, on random interlacements, on free boundary problems, point processes in a broad sense, as we will see in the talk. He has received several awards for his scientific work, like the Guggenheim Fellowship. He got the Consecration Award of the Academy of Exact Physical and Natural Sciences of Buenos Aires, and he was named a Fellow of the International Statistical Institute. And today he will speak about the box-ball system, about solitons, and the Pitman transformation. Please, Pablo.
Okay, thank you very much, Eva, for the nice introduction. And thank you, everybody, to come here to listen. And the organizers and Bernoulli Society and IMS for inviting me to give this honor DUP lecture. I think that my title was wrong, essentially, because I think probably the three things that are mentioned there are not known for most of you. So I decided to start with this picture that the idea of this, half of this talk will be dedicated to relate this picture with the title of the talk, and the other part will be a representation that cannot be drawn here, but I hope that you will appreciate. Okay, so the title is Solitons of the Continuous Box-Ball System and the Pitman Transformation. So this work started with Chi Nguyen, Leo Rolla, and Min Wang, kind of 5 years ago, that we were working in the discrete setup, and we produced this decomposition in solitons, and showed that the dynamics of the composition is linear, and also related with this Pitman transformation, and in parallel, Kuniva and collaborators and Croydon and Zasada were doing complementary work around that. And the work that essentially we talk here, in some sense, reviews the previous work, but from a continuous perspective that in some sense gives more clarity to the various facts, in particular the fact that we have this soliton conservation with the dynamics. So this work, the second work, is doing with Inés Armendariz and Pablo Blanc from Buenos Aires and Davide Gabrielli from L'Aquila. Okay, so I start with what we started that 5 years ago, that this box-ball system that was introduced by Takahashi and Satsuma in 1990, that is a transportation model with solitons. So this is the discrete model. So to each z in z, in integer z,
we have a ball, and a ball configuration is a function that to each set gives 0 if there is empty box, or 1 if there is a ball at this box. And then you have a carrier that, so this is configuration eta, in the upper configuration is eta, and I put the ones in red just to differentiate them. So the carrier is visiting box by box coming from the left, and then picks all the balls that that encounters, and if it has any ball and this is an empty box, it deposits a ball there, one ball. You can have at most one ball at each side. So the carrier here is empty, arrives here picks one ball, has one ball, and deposits in this empty box, then picks these two balls and deposits in these two empty boxes, then comes empty to this box, then picks these three balls, deposit one here, but here he has to take another ball, so it still has three balls, and deposit them here. So in some sense, this is like, you can think that the balls in the first line are arrivals, and the zeros are services, intended services. And at each time, you can have or an arrival or a service. So if you want to look at this as a queuing system, and so when there is an arrival, the carrier load increases, and when there is a service, it decreases, but it cannot decrease below 0. So you have 0 for the carrier load. So I call T eta the configuration below, that is the configuration after this interaction. Okay, so here you have a simulation, manual simulation, of a configuration that has zeros and ones, and in each line you have an iteration of the system, and I put colors, but the colors do not interfere with the dynamics, and you can see that the behavior of these colored objects is the same as a soliton. A soliton is a solitary wave that travels at constant speed and shape, and after interacting with other solitons, maybe changes locally the position, but continues then with the same shape and speed. So these solitons are two solitons that are traveling at velocity 2, and these are solitons that are traveling at velocity 1. They do a mess here, but then after all this interaction, they appear here with exactly the same configuration they have here, but with a shift in the velocity, because you see that the velocity here was 1, and after the interaction, they gain some space. Okay. So, but I will give the continuous thing, so I don't like summaries in the talks, but here I am obliged somehow, because this talk will have 4 parts. One is statics, that is a most boring one, but I have to define things in order to show the results. So I will analyze this zigzag path, and will give you a lot of properties and objects that are hidden in those paths, like records, excursion, solitons, identification, slots that are places where I can put solitons, etc. Then the second is dynamics, and only there I will define the BBS that was shown in the previous transparency, and will show that the solitons are conserved, and I like this, the proof that I am going to give here, because it's very conceptual and very short, and is, I hope, easy to understand. That the previous proof, there existed previous proof of that, but they were pretty complicated. So, and then I will show that when you decompose this path and this gives you a point configuration, so a subset of R2, and you iterate with this box ball system the path, and then you get the representation of this other thing, you see that the new point configuration is just a translation a hierarchical translation of the previous configuration. So in each line, you have a translation. And then only that, then something that belongs to this Congress, that is a randomness. So I show that I will define two families of measures that will play the role as initial measures. One is weighted solitons, and the other one is a transformation of the Poisson process. Show that under certain conditions, these are the same. And using this result, I will show that there is a huge family of invariant measures for this continuous BBS or for the Pitman transformation that is the same. And finally, if I have time, I will talk about the hydrodynamics, that is when you rescale space and time in the Euler, so with the same parameter, and show that this responds to a family, generalized because it's a family of differential equations, one for each conservation law, that are all these solitons are conservation law, are conserved. So you have an equation for the position of the speed of each of those solids. Okay, so let me start with statics. So we will consider three configuration types. One is just a ball configuration. Now will be a function from R in -1, 1, that is pictured here. So -1 will be an empty box, and 1 will be a ball. It's like that. And then from that, I define a zigzag walk that is C, that is this one, that has eta as derivative. Okay, so when eta is -1, goes down. When eta is +1, goes up. And then I define the past minimum. So it's the minimum of the walk from all the past. Defined here is the infimum xc of x or x less than z. And I assume that you have all that is well defined, so that the path is coming down somehow, that you don't have things like to the left of this point. So the minimum will be this line, black line here. And then the carrier load is just the is zeta of z, will be c of z minus m of z. So all this black part here become 0 here, because this is when the carrier load arrives to 0. Even if there are intended services, you cannot produce them. Okay, so a record here, the records play an important role. So record y is the first time that we'll call ry that the process c of z visits y. Okay, so that means that this path is always above y to the left of the origin. Well, I put the origin here, but it doesn't matter much. So, okay, this is the records, and then from the records, the records here are all these black parts. That, in fact, they live here. Okay, they live in the time axis for this path. If you think that this path is the path of a walker, say, or zigzag walker. But nothing random yet. So the set of records I will call R, and R of Y is the set of, there is a record for each level Y. Okay? So the excursion attached to a record is this one. So you have a record here, and then R plus is this position. And in this position, the path did a jump, and all what is above that, these 2 points is called excursion. Okay, so you can the excursion play an important role here, so I will need to parameterize it. So this excursion is, well, it starts at a point A1, say, that is a minimum of the path, and then goes up to a maximum, the first maximum, then the second minimum, and so on, okay? And finally, there is a last maximum, and then there is no minimum here. The path goes down here, okay? So I will call En the set of pairs of sets A and B, because A and B are considered sets, and A1, AN are the ordered names of the points when they are ordered. And in such a way that this gives you an excursion. So you need to have that each minimum is bigger than A1 here. This is what is said here. And so epsilon of AB will be the zigzag walk with minimums at AI and maximum BI. Okay, now I will identify something that is called a soliton. So suppose that you have an excursion, and the excursion is finite, so there is a finite number of minima and maxima. And then I call run the segments that go from a minima to a maxima, or from a maxima to a minima. So I have 4 runs here, and then I have, if you want, I have a run, an infinite run coming here, and this run actually doesn't finish here. It's a semi-infinite run here, continuous here. Okay, now you identify the shortest run. The shortest run in this picture is this one, is BA. The run has 2 extremes, B and A, that can be the first in any order, okay? So the shortest run here is this one, BA, but I represent it directly on the path, because if not, you cannot see it. But the run lives in the axis in the time axis here, Z. And then, once identified the shortest run, I call the interval centered at the maximum with radius equal to the difference between the maximum and the minimum. So this red thing here as a soliton. Okay? This is the first soliton. So shortest run, take the maximum of the shortest run, take the interval with radius equal to the difference between the maximum and the minimum, and this is an interval, so a soliton is an interval in the time axis. Okay? And so here is the definition. I call it gamma 1 now. So it's B minus L, B plus L, where L is the distance between the maximum and the minima, or B minus A in this case. Okay? Well, now I want to, identify one soliton. Now I want to identify the next soliton. So what I need to do to identify the next soliton is to make disappear this first soliton. Okay, so essentially what I would like is to identify this point here, this black-red point here, with this black-red point here. Okay, and this one with this one. I want to do that. But I don't want to lose the position of the soliton already identified. So instead of putting an equivalence relation between these 2 points, I just put a distance that gives a new, I take a new space that instead of being R here, I take R minus this soliton. And I put the Euclidean distance in this new set, saying that the distance between this extreme of the soliton and this extreme of the soliton for the new distance is 0. Okay? So I have a new space a new space and a new distance. But when this new space and this new distance, then I apply again this same algorithm. I look for the shortest run, take the maximum and the segments Okay, all this, when you want to do it mathematically, is a bit messy notationally, but conceptually easy. So the idea is here is the messy thing. So suppose that I have identified the solitons that are less than a given L, I call gamma L minus, and RL minus is the space R minus all those solitons already identified. And then in the previous case was just eliminating the red, but if I had identified a lot of them, I just take all of them out. Then I take the distance, L minus is the Euclidean distance in this L minus, okay? And then I call the new excursion epsilon L minus of Z is epsilon dz for the Z in RL minus, and then I have the maxima and the minima corresponding to that, okay? So I have this new space, new distance, new excursion, and new maxima and minima. There will be less than before. Okay, so in practical words, what I did was to think that this red soliton is not here, so my shortest run now is starts here, continues here, and finish here, okay? This is the shortest run. And so in the distance d L minus, no? L now is this shortest run. And then the new soliton will have the center at B and radius B minus A, L, A, but in the distance without this red soliton, okay? So you have to buy this, if not, the talk is failed. Okay, so then you iterate, and you get something like that. If you have, for one excursion, you identify first this green soliton here, and then you identify this yellow soliton here. That they, in fact, are segments in here. You can see that, but I am used to look at them directly on the path. But strictly speaking, they are these segments. So this yellow is a soliton, and this green is another soliton. These black are records. Then you have this blue, that is this part plus this piece is a soliton, and then the red one, records, and violet soliton. Okay, so now I have identified solitons in all R for the trajectory that the trajectory must have all records, so meaning that all excursions are finite, and I can do this for each one of them. I can do them separately because the line connecting two excursions is always bigger than this line here. So the line connecting two excursions is never the shortest run. So the shortest run is always inside strictly of an excursion and cannot be the one, cannot include a record part. Okay, now this is a crucial thing, is that there is a soliton exclusion rule. And the soliton exclusion rule, let's look at this green soliton, that is a smaller one. So this green soliton has been produced by this shortest run here, has a minimum and a maximum. Okay, I can displace this soliton here without changing the fact that this is the shortest run, so the green soliton will exist if I displace all in this way. But up to a certain point, that is here, if I go a little bit more than this distance here, then the shortest run will pass to be this one. So this soliton will not exist anymore. There will be a smaller soliton because there will be a shortest run here. So in order to have a soliton of this size, this point A must be a distance if suppose that this is L, must be a distance bigger than L of the center of a higher thing. Okay. This is what I said here. If I take, suppose that you have identified all solitons less than L, and the current run has extreme AB, and the distance, ignoring the previous solitons, is L, then the identified soliton, that is the segment centered at B at distance less than L, must satisfy that it is a distance bigger than L of all the other maxima in this distance, okay? For this configuration. Okay. Now I define the slots. So these are points where an L soliton may be attached, and we just discovered that you can attach L solitons only on points X, that are at distance L from the maxima of the path, ignoring all solitons, even or the solitons of length L. Okay? So in words here, in this picture, you can see for the green soliton that is here, you can put the green soliton in all these parts, but not in the top of this other soliton. So I have to cut the top of those mountains. I cannot go there. I have to put it in this. So when you project the place where I can put this green soliton, I obtain this segment that is where I took away segments of length 2L centered at the maxima of the other maxima. Centered at the maxima, at the other maxima, okay? So I call these L slots, where L is the length of the shortest run associated to the soliton. So an L slot will be a record, because a record satisfies automatically that, or it is a DL distance bigger than L of the maxima of XL. This distance HL ignores solitons less or equal than L, and regions near the maxima by less than L. And here you have a picture where you have, for each height here, you have the green part is where you can attach solitons of this height. For instance, blue, you can attach blue solitons only at records here, but you can attach yellow solitons at all these points here, but not here, because here is already a yellow soliton. You cannot put here. But then you start again here, you can put here, and then you jump here, okay? And the violet thing, you have to avoid all these regions. And you get this. But I have simultaneously for all L, given a path, I have a place where you can attach solitons of length L for all L. This is the construction of the previous picture that I jumped. And then I have attachment slots in escutcheon. So suppose that you have an escutcheon with epsilon of 0 equal to 0. And the attachment slot of an L soliton gamma is defined by U gamma is the distance between 0 and the infimum of gamma. In this picture, for instance, this soliton here is attached at this point, that is an L soliton, and the distance is the sum of the length of these three segments that gives you this segment here. Okay? So to each soliton, I have a distance in his distance length to the origin. Here you have a picture for the other soliton. So for the green soliton, I have this distance. To the red soliton, I have this distance. To the violet, I have the sum of these three, that is here. That gives you that. And to the yellow, I have this distance. OK, with that in hand, I define a slot diagram of the excursion. So I have the excursion, have three solitons, this excursion, and I look at the distances in the slot distance for each one of them and put in the horizontal coordinate, and in the vertical coordinate, I put the height of the soliton. So from this excursion, I construct a subset, discrete subset, so having the same number of points as solitons of R2. So in the horizontal, I put the attachment slot in the distance L of gamma, and in the vertical, I put the length of the soliton. These space diagrams have a restriction, is that the points that are inside the diagram must belong to the to some slot produced by the previous, by the higher points. So the first point, L, so for this slot diagram, this first point produces L slot at the speed 2. This is the inclination of this is 1/2, so the speed is 2, and are creating slots for all this L. Finally, you are looking at this, looking down horizontally until you find the first point. And when you put this point contributes with a slot also at the speed 2, but you have to sum them. So this red triangle goes at the speed 4 here and the speed 2 here, until you find, and then you go down until you find the third point. And this third point also goes at the speed now 6 and 4. And finally, the slot diagram is, the contribution is the sum of three triangles that have height L1, L2 for the second thing, and L3, and bases 2L1, 2L2, and 2L3. And this, the slot diagram, so, and whatever is outside there does not belong to this slot diagram, and so it cannot be used for the excursion. Okay, so for infinite path, you have the zigzag path for an infinite path, and then you have excursions, infinite excursions. So for each excursion, you construct your slot diagram here. So this is slot. I am cheating a bit here in the picture, but this is supposed to be the slot diagram of that. This is a slot diagram of that, and so on. But this is empty space. Here is a distance. So now you push all these slot diagrams in such a way that the distance between the end of one slot diagram and the beginning of the following is maintained at all here. Here, this distance is always the same. Okay. And the same between the second and the third, and so on. So finally, if you erase all that, you get a point configuration here. And altogether, and then you can come back. You can come back looking first for the, you observe, but to come back, you observe the configuration down until the moment you find the first point, that will be this one. And then from this one, you start growing at the speed 2 until you find the second one, and then in that way, you construct the first thing. Then you push everything again and construct the second excursion. So, okay. Finally, after doing all that, I get if I have an infinite path that has all excursions, I construct a point configuration C. This one does not correspond to this one, it's just illustrative, okay? And second, the same construction works for negative x. And this is analogous. So altogether, I have a map that from a path C, I construct a point configuration n of C, and then I can construct from n of C, I reconstruct a path C and find the, so it's a bijection. This is analogous to the discrete thing, but in the discrete, we have a collection of independent random variables, the independent collection of variables for each soliton size, because the solitons were discrete also there. Here we have solitons size continuous. That was a paper with Nguyen, Rolla, and Wang, and also Gabrieli. This identification of solitons you can do also using trees. You can map, as one of the sessions today, they were explaining how you construct the tree from an escutcheon. A Brownian escutcheon was in that the case, but this here is exactly the same. And then the slot space is you can construct also in the tree. The disadvantage of the tree is that the dynamic in the path, the dynamics is easy, but the dynamics on the tree is not clear how it works. Okay, now I go to dynamics. So I start the Pitman transformation of walks. The Pitman transformation was introduced by Pitman in 75 in a paper to show the relation between the excursion and the Bessel dimension, excursion in 0, 1 for Brownian motion, and the Bessel 3 process. And then you realize that, in fact, the Pitman transformation is the same as the box-ball system. So, but the definition is the following. So you have Xc is a walk with all excursions, and Txc is Tc of Z is twice the current minima or the past minimum minus eta of Z. That means that each excursion, also you can think that you do that on the records, but to reflect the record gives nothing. So you reflect all the excursions in the level of the past minimum here. Okay, so this point comes here, this point comes here, and then you get the path. I separated it a little bit just for clarity, but in fact these two lines are the same, no? And I put in red the reflected excursions here. So then I copied this path here, and then Txc is this new path that has excursions, different excursions, okay? This is well-defined if all excursions are finite, because we asked that there exist all records. Okay, the BBS evolution, so if you look 1 second to that, you can define the T to the configuration to the derivative, and then you will get that the evolution means that for Z that are not a record for Xc, you just flip the value. So that this means that you just, if you were 1, you go to -1. If you were -1, you go to 1. But if Z is a record, you stay at -1. Okay, a record is always -1. So you flip the values at excursions and keep the values at records. And then you can define it formally using the transformation of the Xc. And also the carrier load evolution, you can do it, but I go fast because I will not need it later. Okay, now here is the soliton conservation theorem that says the following. Suppose that to simplify the statement, I assume that your configuration is finite, or you have a finite excursion. So suppose that you see that this path has an L soliton associated to the DL minus shortest run AB. So you have the shortest run is length L for the distance DL minus, so ignoring all the smaller solitons. But this will happen only if and only if Xi tilde, that is TXC, this is the volvet of Xi, has also an L soliton associated to the D tilde L distance, because the D distance depends on Xi, of course. A shortest run with extremes A equal to B and B equal to A if A is not a record for Xi, and B plus L. Sorry, I will. I am connected now. Okay, so in the picture is easy. So you see that the shortest run is conserved because inside the excursion, when you flip the excursion, the runs are conserved. But the only run that is not conserved is the one that is connected with the next excursion, that is this third case. Okay? When the shortest run I don't know how to do it. It will reappear. Oh. Just, okay, I know what I do. Okay, so you see that here the shortest run are just, when you flip the excursion, the shortest run is conserved in these two cases, and when the shortest run is just, belongs to a record, is attached to a record, that is this case, that means that your excursion has only one maxima, okay? That is this case here. Then the shortest run just jumps to the other thing. So the B tilde is always A, when A is not a record, and it's B plus L, so it's this one when A is a record. Okay. Okay, now I simplified this theorem, so it's the linearization of continuous BBS. So suppose that you have a path C, that is this one, and then you have the linearization, so the representation of solitons given by this point configuration. And then you take the path C and do the evolution. So the evolution of the path C is this path TC. And TC has the representation, these red points here, the representation of solitons. And the theorem says that each red point here is at distance L, that is the height of the red point corresponding to the previous, to the configuration before the evolution. So that means that each soliton in this representation, each L soliton jumps by L forward in the representation. So it's linear, but in each line is just by L, okay? So it's like everything, the biggest solitons go at the speed L, and the shortest solitons also at the speed L smaller. Okay, this was the simple representation. Simplified to R plus because I assumed that there is nothing to the left. I assumed that in this theorem, I assumed that there is nothing to the left. When there is something to the left, you have to be more careful because you need to look at the process from some place. And we are looking here from a record at level 0, And if you look at the record at level 0, it will jump to, it was in this position here, but it will jump to this position here. And you want to look at the configuration from this record 0, so you have to introduce the distance between these two records. So your theta, your translation is linear as before, U plus L, but then you have a correction due to the solitons that are crossing the origin. So the full version of that is that for this new transformation, you have that the process, the point process associated to C as seen from record 0, that means this hat here, is equal to the translation, this special translation of the previous process. Okay, now I have not much time, 5 minutes maybe. We have we introduced two weighted probabilities. One is given an excursion with solitons of sizes L1, Ln, and a parameter family alpha of L with some properties integration. I introduce a measure that gives weights alpha of Li for that Li. The Li are function of the maxima and minima of the excursions. Okay? And Z is just the integration, is the normalization function here. For instance, for the zigzag equation, you have alpha of L. This is an exercise. If you have lambda, you put an exponential lambda plus here and exponential lambda minus to go down. That is classical thing. Then alpha of L is given by that, and Z of alpha is given that by lambda minus. On the other hand, if you have a Poisson process of intensity Q, Q is the vertical intensity. The horizontal intensity is just 1, du. The vertical intensity is Q of L, and Q of L you have asked for the first moment. Then you can define the first excursion of, you take that Poisson process and apply the construction of the first excursion. And then using the properties of the Poisson process, you can obtain a formula, that is this one, that is a formula that factorizes in the solitons slices. So this soliton, I have this equivalence of measure that if you take alpha L is these factors that appear in the expression of the excursion computed with the first excursion of this point process are the same measure. Okay? Okay, so for the zigzag excursion, you can compute explicitly the behavior, the correspondence between alpha and Q. But the important thing is that I can construct these invariant measures, assuming that if you have alpha of L and Q of L related with this formula, and you construct a walk with a record at the origin, and then put IID excursion with low mu alpha, and then excursion separated by IID exponential with integral Q as the parameter, then the slot decomposition of this path is a Poisson process with intensity dx, qy, dy. And reciprocally, if you have that this Poisson process has this intensity and alpha and q are related by that, then the path that you obtain has this property, have independent excursions with low mu alpha separated by exponential intervals of parameter integral q. Okay, from that, you can construct, if you have mu alpha, it's easy to see that that a Poisson process with this thing is invariant for the dynamics of the translation, because you have a process that is translation invariant in the horizontal, and you are translating each coordinate with a different thing, but they are independent. So it's easy to see that this Poisson process is invariant for this process Z here, for the theta process, okay? Okay, then you show that this is an invariant measure for the process as seen from a record, and then you have to do the antipalm measure and apply some Portestone and Harris theorem and show that the translation invariant antipalm measure is invariant and will be T invariant also. Well, I think that my time is gone, so I finish here. Thanks. So this continuous BBS was studied also by Croydon, Sasada, and Tsujimoto, and there are many works for discrete BBS by these people here, and Croydon and Sasada has the hydrodynamics that I was going to discuss, but no time. And there is some linearization that is very similar to the one I did that recently was shown by these people, Muchikoni, Sasada, Sasamoto, Suda, that there is a relation between Kuniva and the one that I was discussing here, for the discrete case at least. And okay. And finally, well, this is, okay.
Thank you very much for this beautiful talk. We started late, so I guess we have time for one or two quick questions. But you have to hand wave such that I see you.
Thank you very much for the talk. So solitons are the smallest hills. Do you also mean the smallest valleys? So that's the first question. And then how does the situation look like for the Brownian motion?
Okay, I didn't understand the first question. The Brownian motion, we are working on that. Yes, it will there is a point process representation of the Brownian motion that has the intensity is going to infinity when you approach the origin. The point is in Brownian motion, the big solitons, they disappear because you are pressing, when you come from you can take it as a limit of this zigzag walk, and then you press there, and so all the solitons, they become horizontal, so the dust solitons are giving you the size of the scarfon.
Thank you. And the first question was, so the solitons are the smallest hills. Do you also mean the smallest valleys?
I didn't understand the question.
Okay, so maybe later. Thank you.
Okay.
The second and last question is over there.
Thank you very much. So, as far as I understand, you do jumps of plus or minus 1 all the time. Would you be able to do, like, replace plus or minus 1 by integer valued random variables? Jumps of plus 2 and minus 3 or something.
You can do that. You can do that for the statics. I am not sure what happens with the dynamics. For the static, you can define solitons, everything, okay. Yes. But then I don't know what happens when you apply the transformation. Maybe it works, but I didn't think about it. Thanks for the question.
Okay, thank you. So I think we should stop here. Thank you again, Pablo. A small gift for your father.
You think so?
And also the...
You have to give it to me.
Okay, good afternoon, everyone. My name is Divi Panaven, and it's my pleasure to introduce Marc Alain, who was selected as one of the medallion lecturers for this World Congress. So Marc Alain is Emeritus Professor at the Université Libre de Bruxelles, Free University of Brussels, where he obtained his PhD in mathematics and has been teaching statistics and mathematical statistics for over 30 years. He also held invited positions at several prestigious institutions, including Princeton University and Paris 6, now Sorbonne Université. He's a fellow of the IMS, a fellow of the ASA, and an elected member of the Classe des Sciences of the Royal Academy of Belgium. He's the author or co-author of over 250 research papers, many of which were published in the best statistics journal, the Annals of Stat, JASA, JRSSB, to cite only a few. He's an expert in asymptotic statistics, non-parametric and semi-parametric inference, time series analysis, and econometrics. The deep contributions he made in those fields were recognized by several important awards. There are too many for me to give them all now, so let me just mention the last two he was awarded in 2022, namely the Gottfried Noether Distinguished Scholar Award from the ASA and the Prix Laplace, that is the most important, most prestigious prize from the French Statistical Society. He acted as the editor-in-chief of several international journals and is presently on the editorial boards of, among others, JASA and the Journal of Econometrics. So Marc, each year, the IMS nominates 8 medallion lecturers in fields across its subject range. The award of a medallion signals the honor inherent in being selected to give one of these lectures. IMS awards the medallion to you and invites you to present a medallion lecture entitled Ancillarity, Maximal Ancillarity, and Semi-Parametric Efficiency.
No, you want to use a headphone? No, I will use that. Is it okay? So I had no idea that the medallion lecture went along with a medal. I'm quite grateful. And of course, it's quite an honor for me to be given this opportunity to give this plenary talk. And it's not just an honor for me, it's a very special thing that this opportunity takes place in Bochum, where I spent in 2012 a most pleasant sabbatical semester on a von Humboldt award. And I have very pleasant memories of Bochum, and I hope I still have many friends here. So thank you, Davy, for this introduction, which is, I'm afraid, a little bit overly friendly. And, well, the work I'm presenting here is work always still in progress, in collaboration with 2 co-authors, Bas Werker from Tilburg University in the Netherlands, and Bo Zhao, who is at Virginia Tech in Blacksburg, Virginia. And since this is an IMS-sponsored lecture, I decided to choose a topic which is quite a fundamental one in mathematical statistics. It's an old problem, very fundamental, ubiquitous. It's almost everywhere, and that's the problem of handling nuisances. And when it comes about handling nuisances, well, the idea of ancillarity comes naturally into the picture. So let me start. No, that doesn't work. Oh, I'm using the, okay.
Just right.
No, that doesn't work.
No, he stopped it. No, not here, so just...
Okay, yeah, but even so?
Okay.
Nothing.
No.
The little joys of computers are
So no.
without limit. Thank you.
No
Thank you. No, still not. Geschlossen.
Sorry. Now it should work.
Thank you. Let me check. Yes, it works. So, as I mentioned, this talk is about ancillarity and the elimination of nuisance parameters. And you... it's not possible to do it by hand.
Let me just take my laptop.
I'm so sorry.
No, we have to be sorry. So this is ridiculous. Kannst du das hier dann weiter bedienen? Ich habe das jetzt gehört.
Yes, and in this talk I will use a little bit of some elements of Le Cam's theory of asymptotic statistical experiments. And I take this opportunity to recall that this year, 2024, we are celebrating Lucien Le Cam's centennial. He passed away in the year 2000. And there will be a celebration in his honor in Paris in November. So those of you who are interested, or those of you who are admirers of Lucien Le Cam, are cordially invited to the Institut Henri Poincaré. I think it's November 18, 19, something, which is the exact anniversary of Lucien, so 100 years ago.
We'll settle this problem. No, so I can take this chance to give you the smell from Ruhr University. It's because we really appreciate that you came all the way to Bochum to present your lecture, Knowledge.
Thank you so much, but I haven't presented it yet, so what if I go away with this?
No. So, and I will just start, yeah.
Wow.
Oh yeah, now people see it.
So.
Yep.
Is it drinkable?
It's
written knowledge.
So
it's drinkable knowledge.
This is perfume.
Perfume.
Yes.
Wow.
So, I told this story for those of you who were not here at the during the opening. So Ruhr University is the only university in the world that produces its own perfume. And this is actually, no, I don't have it on. So this is actually produced by a recipe that is from one of our colleagues in the biology department who is a world-leading scholar in the physiology of smell. So Professor Hatt does that. So now, I think it's...
Thank you
everything
very
is
much.
going. And I will, if I'm going now, then I'm going in order to get my, or does someone have a, okay.
Okay, I assume you will agree that realistic inference problems typically involve nuisance parameters, and the word nuisance tells you all. And often this nuisance is, moreover, an infinite dimensional nuisance. And so the elimination of such nuisances and the construction of nuisance-free statistical procedures is an old problem that has been on the table for, I would say, a century. The concept of ancillarity, as I mentioned, comes naturally into the picture in that context, and I recall that in a model which is involving a family of distribution capital P, so here, I'm not very good at computers, so a family of distribution capital P, which is indexed by two parameters, one theta, which is a parameter of interest, and f, which is a nuisance. Well, we will call nuisance ancillary, or ancillary at theta, a measurable function of zeta, say, of theta and the observation, the distribution under p theta f of which does not depend on f. Okay?
Sorry, I have to interrupt you.
This will hopefully be the last interruption. I don't see how to... okay.
This is at an unusual angle. Maybe there? Now it works.
Okay. And similarly, we will call ancillary or nuisance ancillary sigma field of Borel sets the probability under p theta f of which only depends on theta and not on the nuisance. And in a sense, restricting to nuisance ancillary procedures, which are measurable with respect to an ancillary sigma field A of theta, is the most natural way to get rid of the nuisance F. And of course, the larger the ancillary sigma field, the better, because the larger, the more information. So only maximal ancillary sigma fields should be considered. Maximal here means maximal with respect to set inclusion. Up to p theta f null sets. So I will not continuously, repeatedly say essentially maximal or whatever. Let us always skip this problem, which is an uninteresting one, of the p null sets, the sets that have probability 0 for any value of the parameters. Unfortunately, and that's the problem, maximal ancillary sigma fields, as a rule, are not unique. So there are typically many of them, or several of them, and the question, the natural question is, which ones should we select, and which ones are doing the best job? Which ones are preserving all the available ancillary information in the experiment about theta? This concept of ancillarity was introduced a long time ago by Ronald Fisher, 1925, and he is the one who coined the word. So he introduced this terminology. But the formal definitions and the basic properties about ancillarity were proved much later with fundamental contributions by Bazou. You certainly have heard in your mathematical statistics course about the Bazou theorems relating ancillarity and sufficiency, etc., and completeness. Well, Bazou has written an important paper in 1977 where he emphasizes the role of ancillarity in the elimination of nuisances. And he discusses those fundamental notions I just mentioned of completeness, minimal sufficiency, maximal ancillarity, and the related method of nuisance elimination, but he comes to a somewhat distressing conclusion that no general solution applicable to arbitrary models exists. And there have been more recent reviews, of course, and a more recent one is by Ghosh, Reed, and Fraser, 2010, and they more or less end up, much later, with the same conclusion. So although the problem of eliminating nuisance has been an active line of research for many years, ancillarity remains, and I'm quoting, a shadowy topic in statistical theory, that's by Cox, that continues to intrigue, that's by Gauche, Reed, and Fraser, and despite, and here I'm quoting Bazou himself, and despite an astonishingly large amount of effort and ingenuity, still is strewn with logicians' nightmares. So it's kind of a frightening concept. And in this talk, well, I will try to revisit the problem of ancillarity and nuisance elimination in the light of the asymptotic, an asymptotic approach, an asymptotic point of view, in the context of locally asymptotically normal experiments. And, well, let me give you a typical example. And this typical example throughout will serve as an illustration of what I'm trying to show. And this is the case of models with unspecified residual or innovation density. Namely, these are experiments of the form, so you have this E here, which is you have X, B, and a collection of probability distributions indexed by theta and F. Or, since we are adopting an asymptotic point of view, as we do here, we have a sequence of such experiments, En, with n ranging over the integers. So we have that, in that context, we have that the nuisance F is the density of some residual or innovation driving the data generating process. And that plays the role of the nuisance. More precisely, in such experiments, the observation is of the form x1 up to xn, so it's a sample, or it's an n, and well, you have n observations, not necessarily a sample, because they need not be IID. Let's say they take value in a d-dimensional real space. And there exists a mapping, call it a residual function, mapping the observation and the parameter theta to an n-tuple z, which is such that xn, so the observed n-tuple, has distribution p and theta f, if and only if the residuals z1, zn are IID with density f. So this covers a very large spectrum of classical models, single and multiple output linear and nonlinear regression, panel data, MANOVA, VARMA, long memory and co-integrated time series, etc. And we would call such an experiment, or such a sequence of experiment, an experiment with unspecified residual density, or an unspecified density model. And in such a model, in such models, it can be shown that if you are looking at the sigma field which is generated by the ranks of the first components of the residuals, well, this sigma field is maximal nuisance ancillary. So, well, this follows from a less known result by Bazou, which says that, well, if you have a boundedly complete and sufficient sub-sigma field of the global sigma field, call it A sufficient, and an ancillary sub-sigma field, A ancillary, such that the sigma field generated by the union of these two sigma fields is reconstructing the global sigma field, well, then this ancillary sub-sigma field is a maximal one. Now, the problem is that these are the ranks of the residual's first component, but if you take the ranks of the residual's second component, you have a similar result. You have another maximal ancillary sigma field. And again, for the third component, so you have many of them, and none of them can be increased without destroying their ancillarity. So, big question mark, which one should we go for? Or maybe we should go for something else. This is the type of question I will try to answer. Okay. So, does this puzzle have a solution? Well, maybe asymptotics are offering at least the prospect of a solution. Because as we shall see under local asymptotic normality, we have limiting local experiments. So we have sequences of local experiments that are converging in the Lecam distance to a limit experiment, which is usually described as a Gaussian shift. As we shall see, we will need something more. Well, in these limiting local experiments, well, they are very nice experiments. A Gaussian shift is, in all respects, is probably the most regular statistical experiment you can think of. Well, these limiting local experiments, unlike the finite n ones, admit a unique maximal ancillary sigma field. So maybe if we find a way to construct finite n ancillary sigma fields, which in some sense, to be defined, of course, are converging, and it will be weak convergence. It's not convergent of random variables here, in a sense, converge to this unique maximal ancillary sigma field in the limiting experiment, then maybe we can characterize a finite n ancillary sigma field, which does the job that, for instance, the ranks of the first or the second residual components do not achieve. So let us fix the notation and look at local asymptotics. So now we are looking at sequences. Let us jump to this line here. That doesn't work, no. So we have a sequence of experiments En, which are characterized by a sequence of observation spaces, a sequence of sigma fields, and a sequence of probability distributions. Well, we have the global experiment on line 3, but we construct for each point θ0, f0 in the parameter space, we define from these global experiments, we define local experiments, which are localized at this θ0, f0, and they are indexed by local parameters, theta, eta, taking values in RP product, sum space, epsilon, for the nuisance. So now the parameters are local parameters, tau and eta. I'm skipping the details on how the global parameters and the local parameters are related, but it should be emphasized that the experiment, so the global experiment, the sequence of global experiment for fixed n, and the local experiment localized at θ0, f0 for fixed n, well, they are sharing the same observation spaces and the same families of distributions. So they only differ by the way they are parametrizing the family of distributions. So either with tau eta or with a theta f. And therefore, finite n nuisance ancillarity in the local experiment for given n is equivalent to finite n nuisance ancillarity in the global experiment for the same n. That's important. Now, this problem of nuisance parameter elimination, of course, is central in the classical theory of semi-parametric inference. I'm thinking of the classical monograph by Bickel and co-authors. who also are using a LeCam asymptotic perspective based on the assumption that the global experiment is LAN with some central sequence delta n and an information matrix gamma. Now, as you probably know, under LAN, the local experiments are converging to a Gaussian shift experiment. And in that limiting Gaussian shift, Bickel and co-authors are defining tangent space projections. And the tangent space projections are so looking at this asymptotic experiment, this Gaussian shift, and they are projecting the observation delta in that Gaussian shift onto the orthogonal complement of the space of shifts which are induced by the local perturbations of the nuisance eta. And these projections, call them delta star. So delta star is the result of that projection of delta in the Gaussian shift. Well, the projector depends on the information matrix gamma. So it depends on theta 0 and f0. And the idea behind this approach to semi-parametric inference is that the same projection, which is defined in the asymptotic experiment, is performed on the finite n central sequence delta n. And that yields a delta n star, which converges weakly under the p tau and eta, local parameters tau and eta, to delta star, and therefore inherits the same asymptotic distributions. Now, these tangent space projections do achieve nuisance ancillarity in the local limiting Gaussian shift experiment. Okay? The distribution under tau eta of delta star only depends, but via the information matrix gamma, on tau, but not on eta. Okay, so it is the same as under p tau 0. However, the tangent projection delta stars themselves strongly depend, because of the information matrix which is used to define the projector, on f0, on the nuisance. And when it is performed on the local sequence, well, they achieve, quote unquote, asymptotic nuisance ancillarity, but not finite n ancillarity, neither in the local sequence nor in the global sequence. Moreover, this asymptotic nuisance ancillarity of delta n star only holds if the f0, which is used to define the projection, coincides with the actual value of the nuisance f. So we are in kind of a circular situation, because this f, of course, the actual f, is unknown. That's the characteristic of a nuisance. So the usual solution consists in performing the tangent space projection associated with some estimator, f hat of f. And this yields a delta n star, which is the delta n star associated with theta 0 and f hat. And assuming, this means that the estimator should have some properties, that this delta n star still converges in distribution under Pn tau eta to the actual delta star, in a context where estimation of infinite dimensional nuisances is not easy. It requires kernel estimators, sample splitting, and such things. And moreover, asymptotics are pointwise and highly non-uniform in F. Well, this weakens the interpretation of the result as being asymptotically ancillary. So, of course, this kind of solves the problem, but one, this tangent space approach is limited to one statistic, which is the projected central sequence associated with this f hat and its linear transformations. Second, it requires an adequate estimation of the nuisance, which is unpleasant. And third, it only achieves pointwise asymptotics. Now, if we assume that the limiting experiments under LAN admit a unique maximal ancillary sigma field, this sigma field will measure delta star, but much more. And assuming that a sequence of finite and ancillary sigma fields can be constructed in the sequence En, which in some sense, some appropriate sense, converges to that unique maximal ancillary sigma field, well, then the asymptotic performance of any delta n star could be achieved by sequences of finite and ancillary procedures. So we would achieve the same asymptotic performances, but now with finite and ancillary procedures. Okay, and recall that finite n ancillarity in the local experiment is equivalent to finite n ancillarity in the global experiment. So our objective is, one, to show that under LAN, indeed, we have this unique maximal nuisance ancillarity sigma field. Second, to characterize the sequences of finite n maximal nuisance ancillarity sigma fields that are weakly converging to this unique maximal ancillary sigma field of the limiting experiment. And that will be in the sense that any variable which is measurable with respect to that asymptotic, to that maximal ancillary in the asymptotic limiting experiment, well, any such variable can be approximated weakly, it's always in distribution, by a sequence of variables that are measurable with respect to the finite and maximal ancillary sigma field in the sequence of local experiments. And as an application, we will show that in local asymptotic normality unspecified density models where the nuisance is the density of some noise, well, the sequence of sigma fields generated by measured transportation-based center-outward residual ranks and signs are such a finite and maximal ancillary sigma field sequence, reconstructing the unique one in the limiting experiments. Okay, actually, when such a sequence AN ancillary exists, well, the restriction to that finite n ancillary sigma field of local experiments is converging in the Lecam distance to the restriction of the limiting experiment to the unique maximal ancillary sigma field A. So this means that we are exactly having for finite n an experiment that will asymptotically produce the same risk functions as the maximal ancillary sigma field in the limiting experiment. Okay. Now, limiting experiments. As I mentioned, limiting experiments typically are described as Gaussian shifts. Now, this is not necessarily the only description, because limiting experiments are only defined up to an equivalence in the Lecam distance. So if you have two experiments, and the Lecam distance, which is not a distance, it's a pseudo distance, but the Lecam distance between those two experiments is 0, well, then both can serve as a description of the limiting experiment for the local sequences. And it's the case here that we will need limiting experiments that have a richer sigma field, that are living on a richer sigma field than the Gaussian shifts. And that will be the case for an experiment which we will call a Brownian shift, a Brownian drift experiment. So we have so let me hurry up. We have this sequence here of local experiments, and it is localized at theta 0, f0, and it is converging in the Lecam distance weakly to a limiting experiment, which is this one. Okay? And this one, but if we have another experiment, E prime, such that the finite dimensional marginals of the log likelihood processes, so the log likelihood processes, or the likelihood processes that will make no difference, are the Radon-Nikodym derivatives of the limiting distribution under tau eta with respect to the limiting distribution with respect to 0, 0. And so if we have two experiments, E and E prime, for which these finite marginals of the log likelihood or likelihood ratio processes coincide, then their Lecam distance is 0. So they are equivalent in the sense of the Lecam distance, and therefore they both can serve as a description of the data generating process behind the limiting distribution in the local sense. And this is the description, the classical one, as a Gaussian shift. And I'm skipping details because time is running. And we define another experiment, which is a Brownian drift experiment, which is living on a richer sigma field. And here is the observation for that Brownian drift experiment. It's this delta drift, which is a collection of Brownian motions. And, under 0, 0, so tau equals 0, eta equals 0, we have that these Brownian motions have 0 drift and the same finite dimensional covariance matrices. And under p tau eta, we still have Brownian motions with the same covariance structure as under 0, 0, but now with drifts. And this characterizes completely the distribution of delta drift. And from there, we can show that the likelihood ratio processes have the same the marginal distributions, the finite dimensional marginal distributions of the likelihood ratio processes are coinciding. So we can conclude that the limit experiment described via delta shift as a Gaussian experiment and via delta drift as a Brownian drift experiment, they coincide in the sense of the Lecam distance, and the benefit from considering the Brownian motion, the Brownian drift experiment rather than the Gaussian shift, is a richer sigma field, and we will need this sigma field for our asymptotic maximal ancillary sigma fields. Okay, so let me summarize the sufficiency and ancillarity properties in the Brownian drift experiment. And let us focus on the last two lines here. We have in that experiment that the sigma field, which is generated by the collection of B sub etas, where eta is the local parameter for the nuisance, is the unique maximal nuisance ancillary sigma field in that experiment, that Brownian drift experiment, and these B etas are just the Brownian bridges associated with the Brownian motions associated with the nuisance component of the parameter. So we have this property of a unique maximal ancillary sigma field in the limiting experiment, expressed or described as a Brownian drift experiment. Now let us come to the concept of weak convergence of sigma fields. And so we have still this sequence of local experiments, En, converging in the Lecam distance to this limiting experiment E. And let us first define the concept of a En weak convergence of random variables. And we will say that a sequence psi sub n of Bn measurable random variables, so Bn is the sigma field in the sequence of local experiments, converges En weakly to the B measurable random variable psi, where B is the sigma field in the limiting experiment, if for any finite subset of the parameter values, we have this convergence here in distribution of the, so this is the joint distribution of the likelihood ratio process for a finite collection of parameter values and the sequence psi n. And so this is the definition of this En weak convergence. Note that if psi n is a sequence of constants, this is just the definition of convergence in the Lecam distance. And for sigma fields, so let us consider a sequence An of sub-sigma fields of the sigma field Bn in the local sequence. We say that this sequence of sub-sigma fields En weakly converges to the sub-sigma field A in the limiting experiment if for any A measurable variable psi, so in the limiting experiment, there exists a sequence psi n, which is An measurable, and En weakly converges to psi. Intuitively, this means that you can approximate the distribution of that psi in the limiting experiment by considering sequences of variables which are measurable with respect to this sequence An of sub-sigma fields in the limiting experiment. Now, we will call countably generated a sigma field A, which admits a countable generating family A1, A2, etc. of uniformly bounded variables. And this is the typical case. Think of indicators. So this is a very mild condition. And then we have a sufficient condition for En weak convergence that if A is countably generated by some sequence A1, A2, etc., and if each of these generating A sub k's is the En weak limit of a sequence of An measurable variables, then the sequence of sigma fields En weakly converges to A. Okay, so this is a criterion that allows us to construct or to check whether a sequence a sequence An is En weakly converging to a limit A. And we have then the following theorem, and my time is out, so I will jump to the conclusion. It's a theorem by which we have a corollary that the weak convergence in the Lecam sense of the restriction to An and theory. So yeah, I should say what the assumptions are on this An and theory. So we have this limiting experiment E0, which is the limiting experiment for tau equals 0 and varying value of the nuisance eta. If it is such that its sigma field is countably generated, and if we have that the sequence of local experiments is such that it admits a minimal sufficient and boundedly complete sigma field Bn sufficient, and an ancillary sigma field An ancillary such that the sigma field generated by the union of these two sub-sigma fields is the global sigma field. So this is the result by Basu, which I mentioned at the beginning. Well, we have this assumption, and similarly, we assume that in the limit experiment, we have a minimal sufficient and boundedly complete sigma field B sufficient, and an ancillary sigma field A ancillary, such that the sigma field generated by the union is the complete sigma field for this limiting experiment. This implies that these ancillary sigma fields are maximal ancillary. That's the result by Bassou. Well, then, if we have this weak, En weak convergence of this sequence En to the limiting A, well, we have the weak convergence in the Lecam sense of the restriction to the sequence of maximal ancillary sigma fields of the sequence of local experiments to the restriction to the maximal ancillary sigma field in the limiting experiment E. And we say in that case that the sequence of ancillary statistics AN is strongly maximal ancillary, and then it's the one we should go for. And, well, this has, of course, crucial implications that all risk functions that can be achieved via nuisance-free procedures in the limiting experiment are limits in the Lecam distance, so this means pointwise in the argument tau and uniformly in the collection of risk functions, of sequences of risk functions that can be achieved via finite and nuisance-free procedures in the sequence En. Hence, in the global experiment, E global. Okay, so let me. This is in sharp contrast with the semi-parametrically efficient procedures based on tangent projections, which are achieving the same efficiency bounds, but they are not finite and nuisance-free. They require the estimation of the nuisance, etc. Now, let us turn to the application to unspecified density models. This is an illustration, so let Z be the residual in the sense I defined at the beginning. Well, we are considering the so-called center-outward distribution functions, F plus minus, which are so this F plus minus is the unique gradient of a convex function, which is mapping RD to the unit ball in RD, such that if Z has distribution P, then F plus minus computed at Z is uniform, and uniform here means the spherical uniform over the unit ball. So this is a way of defining a center outward distribution function which has all the nice properties of a distribution function, although it is defined on RD. And in the univariate case, it reduces to 2 times F minus 1. And it can be shown, for instance, that this definition, if you look now at the empirical counterpart is the optimal transport from the observed residuals to some grid which weakly converges, well, the empirical distribution over which weakly converges to that spherical uniform. Well, there is a Glivenko-Cantelli property that is probably the most important property of empirical distribution functions. Now, this grid can be constructed. I skip details. So this is a picture showing how these F plus minus are mapping the cloud of points to the grid over the unit ball. And, it has been shown in 2021 in a paper with Spanish co-authors that the sigma field, which is generated by these f plus minus n, the empirical version, well, these sigma fields are strongly maximal ancillary. But are they strongly maximal ancillary? Well, the answer is yes. And since my time is over, let me just say that, it can be proved via a nice Hayek representation, asymptotic representation theorem, which is due in part to two co-authors who are sitting over there from Charles University in Prague, so well in the Hayek tradition. And thanks to this asymptotic representation theorem, we can show that indeed this sigma field En weakly converges to the right limit. So the conclusions are far-reaching in semi-parametric inference. It really means that semi-parametric efficiency bound can be reached by, in this case, by procedures which are measurable with respect to residual center-outward ranks and signs. And they are finite n distribution-free, that is, ancillary, nuisance ancillary in this case. Okay? So these properties demonstrate the considerable finite sample advantages of considering the conditional expectation, for instance, of the central sequence delta n, conditional on this strongly asymptotically ancillary, nuisance ancillary sigma field over the classical tangent space projection. It achieves the same results, but of course, it's much better in a sense because it's a finite n distribution free, and you don't have to estimate anything like the nuisance density. Thank you for your attention, and I'm sorry if I went over my time.
Thank you, Mark, for this nice talk. We don't have time for questions, but we'll take some time for questions. So one or two quick questions? I will ask one. Yeah.
Thank you for a nice talk. I have two very short questions, I hope. So firstly, I'm here. Is there any role here for singularities? If I understood you correctly, part of this depends on some rank assumptions. Would it be possible that some rank deficiency would affect the convergence of the construction of the sigma fields? And secondly, is there any role of optimal transport? You mentioned it twice or three times. Is there any role in terms of the procedure? Thanks.
So the rank in the sense, what do you mean exactly with the rank of what? The ranks of those residuals? Yes, okay.
There are some problems in terms of the starting assumptions. So there would be problems with ranks.
Okay. Yes, I oversimplified the definition of these residuals. And for instance, in time series situations, you need to construct n residuals. You also need some starting values. But the asymptotic, under very general assumptions on the model, such as stationarity or whatever, you have that the influence of those starting values is negligible in the limit. And so in order not to make things too complicated, I just assign the same n for the n-tuple of residuals as for the n-tuple of observations. As for measured transportation, well, just think that the ordinary distribution function in R is just the only monotone transformations, pushing the distribution P forward to a uniform here over the unit interval. Now, a unit interval in dimension 2 and higher is a bit delicate, and we rather go for a center-outward approach. But the idea eventually is exactly the same. You are transporting the measures to a uniform one, and the inverse mapping is a quantile function.
Okay, well, but in the interest of time, I think that we will need to stop the discussion here. But we would like to close actually with an announcement. And for this, I call Siegfried Oermann and Matteo Marigozzi. Okay, so we'd like to actually, maybe you open the file. Open the file. So we'd like actually to inform the audience that a Festschrift volume, a Springer Festschrift volume, was actually edited in the honor of Marc and was edited by Matteo, Siegfried, and myself. The book is in press and can actually already be pre-ordered. So, Marc, we would have loved to offer you the book today. Unfortunately, it's not ready, but we have a pre-version of it in which at least you will be informed about the long list of contributors and the title of the contributions. And yeah, so we offer it to you. And meanwhile, of course, please join us in thanking Marc for his Medallion lecture.
welcome. Can you all hear me? Great. We had a little bit of a technical delay there. But I'm Michael Kosruck. I have the privilege of being president of IMS right now. And I want to welcome all of you to the IMS Award Ceremony and Presidential Address. And I'm the current president of IMS. I also want to introduce three other individuals. If they could please stand. Tony Kai, President-elect. Peter Bullman, past president. And Kavita Ramanan, the incoming president-elect. The first thing I would like to do today is to thank our outgoing past president, Peter. I want to give you a little bit of background and just say a few things. He's been a professor in mathematics at ETH Zurich since 1997, and he chaired the department from 2013 to 2017. He's elected member of the German National Academy of Science and a fellow of IMS, and he has many additional awards. He was co-editor of the Annals of Statistics from 2010 to 2012. He has 40 PhD students at least in his career, and he has an astonishing Google H-index of 85. He has many research contributions, especially in many areas, but some areas I highlight are random forests, and his MIS-forest work is highly used and considered by many the standard for non-parametric multivariate missing data imputation. In his role as IMS president, he was absolutely outstanding. For him, the most rewarding aspects have been communicating with and getting to know many, many interesting people in IMS with different views and cultural backgrounds. He really enjoyed interacting with people, and this is very obvious from those of us who observed him. He initiated an important new item in IMS, the Industry Friends of IMS. It's still in its infancy, but this recognizes a crucial role of collaborations between academia and industry in statistics and data science. This is a new IMS membership category. Personally, I've really enjoyed working with him. He is kind and wise, a wonderful human being, and I have always found his counsel to be very valuable, and still do, and probably always will. Thank you, Peter, for your service.
Thank you very, very much.
Thank you.
Okay.
Thank you. I also want to thank the chairs for this planning for the 2024 World Congress from the IMS side of this. And if they're here, could they please stand? Aurora DeLagle and Kavita Ramanan as program chairs, and Harold Daling as local chair. Thank you. I want to take a moment to acknowledge members and leaders in IMS who have passed. And I'd like, before we begin the presentation of their other awards, I'd like to take a moment of silence to remember the members and leaders of our community have passed this past year. And I'll give their names here. Peter J. Brockwell, Shuter Kishore Chatterjee, or SKC, Teo Gasser, Dick Gundy, Alan Hawks, Anand Kishore-Sagar, Johannes Ledalter, Colin Mallows, Richard A. Olson, Donald Pierce, R.V. Ramamurthy, C.R. Rao, A.K.M.D. Asana Sala, Kasala Subramaniam, Wolfgang Weffelmeyer, and Ruben X. Zamar. The IMS has many awards that it bestows on both members and non-members. This award ceremony tonight is to present those awards that are for service to the profession and our travel awards. Awards that are given for special lectures are presented immediately before the special lecture itself.
The Carver Medal was created by the IMS in honor of Harry C. Carver, founding editor of the Annals of Mathematical Statistics and one of the founders of the IMS. We are presenting the 2023 medal in person this year, and we will present the 2024 medal in person next year. The recipient of the 2023 Carver Medal is Leif Döring, for his initiative and vision in organizing the Bernoulli-ims One World Symposium in August 2020, when the COVID-19 pandemic forced the IMS and Bernoulli Society to cancel their previously planned 10th World Congress in August 2020. Professor Döring, jointly with a small committee, created this meeting out of nothing. The symposium was a great success, trialing a number of new ideas with a special emphasis on new researchers, as well as exciting live talks with more than 600 videos uploaded and 3,000 registered participants.
Everybody can see that. Congratulations. You're very welcome. Thank you.
So those who are named IMS Fellows have demonstrated distinction in research in statistics or probability by publication of independent work of merit. Fellows may also be well-established leaders whose contribution to the field of statistics or probability other than original research are of equal or great value, or their work has contributed greatly to the utility and appreciation of these areas. And we will be presenting the award to the fellows who are able to be here tonight. When your name is called, please approach the podium to receive your award. The first one is Morgzata Bogdan for innovative contributions to high-dimensional statistics, particularly in multiple testing and variable selection, for insightful connections between Bayesian and frequentist approaches, for successfully integrating methodological work with applications in genetics, and for leadership in fostering scientific collaborations. Next fellow will be Maria Godina for significant contributions to stochastic analysis and stochastic differential geometry and service to the IMS. Our next fellow is Edsel Adia Pania for important and significant theoretical and methodological contributions in modeling and analysis of event time data, multiple decision-making, reliability theory and methods, goodness of fit and model validation, effective teaching and mentoring of graduate students, and for dedicated service to the profession. Our next fellow is J. Sunil Rao for novel contributions to high-dimensional model selection and mixed model selection, developing new paradigms to modernize mixed model prediction, developing innovative statistical and machine learning methods for analyzing cancer genomic data, and demonstrating significant leadership in their profession. The next IMS fellow is Johannes Schmidt-Hieber for pioneering work on the statistical foundations of deep learning and fundamental contribution to spot volatility estimation, non-parametric inference and shape constraints, high-dimensional Bayesian inference, Lacan theory, and the inverse problem. And the next fellow is Piotr Zwernik for outstanding contributions to the theory of graphical models, exponential families, multivariate positive dependence, and dedicated editorial and organizational service to the profession. And we also have many new fellows who are not able to be here today. And you can read on this slide and also read their citations on Bulletin or on the IMS website. I also want to take this occasion to announce the Pete Hall IMS Early Career Prize Award. And Peter Hall, as many of us here knows him personally, played a significant role throughout his professional career in mentoring young colleagues at work and through professional society activities. And the purpose of this award is to recognize early career research accomplishments and research promises in statistics broadly construed. And the 2024 recipient of the Peter Gavin Hall IMS Early Career Prize Award is Edgar Dobreben for deep, fundamental, and wide-range contributions to mathematical statistics and statistical machine learning, including high-dimensional asymptotics, ridge regression, PCA, multiple testing, randomization tests, scalable statistical learning via random projections, and distributed learning, uncertainty quantification for machine learning, calibration, prediction sets, robustness, fairness, and testing via hypergraph factorization. And Edgar is my colleague, and he's not able to come today, but we extend our congratulations to him. Next, I want to invite Peter Buhlmann to the podium.
So we come now to the announcement of the IMS Hannon Graduate Student Travel Award and the IMS New Researcher Travel Award. The purpose of the IMS Hannon Graduate Student Award and New Researcher Travel Award is to fund travel and registration to attend and possibly present a paper or poster at any IMS-sponsored or co-sponsored meeting. The following IMS members received awards in 2024. If the award recipient is present tonight, please stand when your name is called. Following tonight's presidential address, we're asking the awardees that are present to meet here by the stage for a group photo. Please hold your applause until all awardees are announced. The 2024 Hahnengradet Student Travel Award recipients are Li Jua Bai, no applause, Heng Chao Chen, Yun Cheng Dong, Yi Hong Gu, Chi Rui Hu, Sung Woo Kong, Dob Seong Ki, Dong Woo Kim, Chang Woo Lee, Sung Yoon Lee, Kwang Moon Park, Ann N. Shapiro, Song Hua Tang, Fan Wang, Zhong Wang, Max Welz, Shi Hao Wu, Xintao Xia, Wan Zhang, Yikun Zhang, Yuming Zhang, Fan Zhao, Yidong Zhou, Junhao Zhu, Wanrong Zhu, Jihan Zhu. So you see we have a lot of diversity here in different names and culture. That's really great. And the 2024 IMS New Researcher Travel Award recipients are Naha Agarwala, Sotarupa Bhattacharjee, Biao Kai, Michele Caprio, Kan Jun, Mingyue Chu, Beatrice Franzolini, Andrea Gilardi, Siyu Hong, Haishiro Kanagawa, Bingkai Wang, Shuoyang Wang, Haiyan Yu, Mengxing Yu, Yuchen Zhou, Tiana Zernik. So now I think it's time to applaud and applause all these. And I recall again after the presidential address, the ones who are here, please come on stage for a great group photo. So I have now the pleasure to introduce the presidential address speaker, the IMS president. And it's my great pleasure to do this. I should say already at the beginning, I very much enjoyed working with the 88th president of the IMS, which is Michael Kosarok. So Michael has a very interesting career path, which I would like to point out a bit. Of course, in this short time, it's impossible to acknowledge all the great contributions which Michael did, but I picked a few and want to introduce him this way. Actually, the first degree which Michael Kosarok got is a Bachelor in Music Composition in 1988. The same year, he received a Master's in Statistics. Then he moved to the University of Washington in Seattle, where he did the PhD, but before that he gets a degree, a master's degree in biostatistics, and then the same year in 1991 he gets the PhD in biostatistics. Quite a few years later, he gets an additional degree in 1999 when he is already at the faculty of the University of Wisconsin in statistics, biostatistics. In addition to his faculty position, he manages to get another degree, a master's degree in music composition. So as I indicated already a bit, so Michael did his PhD in Seattle at the University of Washington in 1991, and then he moved to the University of Wisconsin and worked there from 1992 till 2006. He was appointed as professor in biostatistics, statistics, and pediatrics. He went through the usual career. He was assistant professor, then associate professor, then full professor. But not only that, he was at the same time also employed as a biostatistician in the General Clinical Research Center at the University of Wisconsin. Then he moved in 2006, he became professor of biostatistics and statistics and operations research at the University of North Carolina and Chapel Hill at the UNC, where he is still today. What's very impressive about his career path also is at UNC, he served as department chair. But he didn't serve just for a few years. He served for 13 years. It's just an incredible long time. I'm sure people wanted that he served so long, but it shows also his huge dedication to his university, his department. I'm truly amazed. 13 years being chair of a department. Since 2013, he is distinguished professor at the University of North Carolina in Chapel Hill. Michael's contributions are very multifold, and I picked two streams of contribution, namely research and music composition. In research, Michael is very well known as a famous biostatistician. He also does a lot of modern things, data science, machine learning, artificial intelligence. At the same time, he's doing very solid mathematical work on empirical processes, and his work really is shining into the applications. He is involved in precision medicine, precision health, and precision operations. He wrote a very influential book, Introduction to Empirical Processes and Semi-Parametric Inference. This has been published in Springer. He wrote very many great papers, and this is not the right place to list them all here. But also I would like to point out, he actually leads the UNC's Precision Health and AI Research Lab. And so this is really very amazing how broad his research interests and his research contributions are, combining from mathematical rigorous theory to very, very relevant biomedical applications. So he really pushes his work through and makes it applicable in very practical setting. I think this is truly amazingly broad. Now, I'm a bit less an expert in music, but I looked a bit, tried to understand a bit what Michael's contributions are in music, and I just show you pictures. I thought, okay, we're not playing audio here, but in pictures, Michael is still very active in composing music. Here is a piece. It's called Prelude 2. It's composed very recently in February 2024 for piano. That's how it looks like. But it's not only composing for a single piano. He actually composes for whole symphony orchestra. Just recently, in January 2024, that's how it looks like. It looks pretty simple, but no, hold on, it becomes much, much more complex. It's for a whole orchestra. He's able to manage the complexity to compose for a whole orchestra. So I looked a bit on Michael's webpage, what he has in music, and he writes, and I quote Michael's writing, "I write in the classical tradition with an eclectic mix of stylistic influences, including modern, classical, new music, serial, Renaissance, Baroque, jazz, folk, and other influences. I compose part-time, logically, mostly evenings and weekends. Just truly impressive that you can manage to be a great researcher, IMS president, and composing music. I'm simply baffled by this. Awards and honors. Michael received very many awards and honors. I just mentioned a few. In 2023, he got the George W. Snedecorn Award from COPS. In 2019, the Gottfried E. Noether Distinguished Scholar Award from the ASA. He's Fellow of the American Association for the Advancement of Science. He's Fellow of the Institute of Mathematical Statistics. He's also Fellow of the American Statistical Association, and he was also a medallion lecturer at IMS in 2015. He gave numerous plenary and keynote talks. That's not the place here to list them, but he has a very, very distinguished research career. Educating and supporting young researchers. Michael mentored, according to the CV9, postdoctoral fellows, and he advised and co-advised 60 PhD students. You certainly left a big trace, Michael, to the next generation of scientists. This is one of the greatest contributions we can do. As IMS president, I got to know Michael as being conscientious, skilled to balance views, and prudent and kind. But that's not quite right. I got to know him as very conscientious, very skilled to balance views, and prudent and very kind. I very much enjoyed working with you, Michael. It was wonderful to get to know you much better. Thank you for all your great and excellent work as a wonderful IMS president. And I welcome you now on stage to present your IMS presidential address.
I'm not sure I can follow that or even want to follow that. That was phenomenal. I certainly don't know if I can live up to that. I'm not sure who he was talking about, actually. But I'm very honored to talk to you about some things. I've really enjoyed working with Peter. Thank you for your kind words. So, as you all know, IMS is focused on fostering the development and dissemination of the theory and applications of statistics and probability. We've been around for a long time. Next year, we celebrate our 90th anniversary. And so here's what I want to discuss a little bit. I want to talk a little bit about my personal journey with IMS. I want to talk about what IMS does. What does IMS do? What does it do? I want to talk a little bit about the people of IMS, including you and me. I want to talk about all of us as researchers, including the big picture, the role of critical thinking, and who gets to decide the important questions in research. I also want to talk a little bit about data science and artificial intelligence, and also a little bit about how we're going to go forward. So first off, just a few personal views. I remember as a young assistant professor, I was primarily in statistics and jointly in biostatistics at University of Wisconsin-Madison. I really thought highly of IMS. In 1998, I decided I really wanted to do work in empirical processes. And as I began to be a little more focused on the mathematical statistics side of my work, I really set a lifetime goal to become an IMS fellow. As one of many goals, but IMS fellowship, I felt that target was very good for the career trajectory I wanted to achieve. I had the privilege of organizing conferences for IMS as program chair or co-chair, 2002 Wiener IMS, 2006 ENAR IMS, and 2009 IMS JSM, getting to know and work with the wonderful people of IMS. It was just the wonderful conferences that our IMS is a part of. I had the privilege of being an associate editor for Annals of Statistics from 2004 to 2021. And then I had the privilege of becoming a fellow in 2007. So what does IMS do? All of you are here as part of IMS, and you know many of the answers here, but I just want to mention a few. IMS helps organize, promote conferences that are helpful in disseminating research and in promoting people developing their research career. We have outstanding publications, several journals. All of you know Annals of Applied Probability, Annals of Applied Statistics, Annals of Probability, Annals of Statistics and Statistical Science, as well as monographs and lectures, and other publications that we play a significant role in, including the important IMS Bulletin, which does a superb job of telling us what the people in IMS are doing and what IMS is doing. As I mentioned, also supports other journals and publications. And this is really a rich tradition because many of these journals are the absolute top in the field, as you all know. Another wonderful thing it does is supports new researchers. And there are many ways it does that. I won't go into all the details. I'm just talking at a high level here. The other thing is providing professional awards to provide recognition for the tremendous accomplishments of the people of IMS. I think also from a broader point of view, we actually help to define and improve the fields of statistics, probability, applications, and by statistics I include mathematical statistics, just want to be clear about that, probability, applications of both, and related research areas. We help to establish a culture of rigor in these areas through our journals and our conferences. I feel we have a very strong reputation for rigor in the research that we do. And that's an important part of the IMS culture. Okay, I want to talk a little bit more about some of the people of IMS now. I want to acknowledge Elise Gustafson, who is actually the leader of IMS. The rest of us work with her, but she does tremendous work as the executive director. And Taddy Howell, who does the IMS Bulletin as IMS Bulletin editor and many other things to help us. The publications, Patrick Kelly, Jerry and Chrissy Matson, and administrative support, including Lila Lunderman and Lissa Purrier, who help with the website and also with membership. Other people that are an important part of this are the past president now, Peter Bullman. As I've mentioned before, he's wise and patient, remembers everything. He's an outstanding researcher. He's very kind, and I mean those in the extreme sense as well. I also want to acknowledge President-elect Tony Tsai, Treasurer Jishin Jin, Program Secretary Annie Chu, and our Executive Secretary Peter Hoff. Those are members of the Executive Committee. In addition, we have the, I think I skipped a step. Yeah, we have the IMS Council, which includes the Executive Committee, plus our IMS editors and co-editors for our 5 primary journals, elected council members, 15 of them, and we have many IMS committees. We have 18 standing committees, possibly more, but those are the ones I could count. And there's over 150 committee positions. So I want to acknowledge all those who play a role in those various organizations. We have, at this moment, 4,700 members. It's an increase from last year. And we also have all of the people we collaborate and work with and are all of our students. These are also people that are affected by IMS. So a few of the committees I want to just mention are Asia Pacific Rim Meeting Committee, IMS China, and co-sponsorship committees, the Brown and Zellen Awards committees, the Hall Prize and Travel Awards committees, Equity and Diversity committees, the Professional Code of Conduct Committee, Fellows Committee, Special Lectures, Finance, Memorials, Publications, Outreach Committee, Nominations, Selection of Administrative Officers, and Selection of Editors. Those are all committees that we have in the New Researchers Group as well, and I'm missing a few of these, but I just wanted to give you a high-level idea of the tremendous amount of things that IMS does. All right, now I'm going to switch topics to looking at us as researchers. I don't know how many of you have presented a talk as a president of an organization such as IMS. What sort of things should you talk about or should you discuss? And I went through many times thinking about these things. I can't talk about my own research, that's not the appropriate venue, or actually individual research going on. There's a tremendous amount. How would I possibly be able to choose? Anyway, so I want to talk about just some perspectives about research that I have been thinking about the last couple of years. And I want to provide some perspective. I was introduced to a very interesting, provocative article, The Importance of Stupidity in Scientific Research. I'm pretty sure that wasn't taught to you as a student, but let me be a little more clear about what I mean here. This is tongue-in-cheek, but there is an important message here. The person who wrote this article, which appeared in the what journal was it? A Journal of Cell Science. Martin Schwartz is a distinguished professor of medicine, cell biology, and biomedical engineering at Yale University. He has an H-index of 124. He's very accomplished in his field. And he had a story that he related when after he'd been fairly successful as a professor, he tracked down one of the people that was in the lab that he worked in. This was a very talented woman, and she dropped out of the program, and it puzzled him because she seemed to be the smartest one in the room. And he asked her, why did you drop out? Why did you stop? You're doing so well. And she was successful as a high up in a law firm, so she had a successful career, but wasn't in science. And he asked, why did you drop out? You were like the smartest one of all of us. And she said, I was tired of feeling stupid every day. And I think this is a really interesting point. And I feel that as researchers, we subject ourselves to a lot of situations where we don't understand what's going on, right? Some question we want to answer. And our PhD programs, at some point, we realize that no one actually knows the answer to the question that we're asking. That's why it's research, why at the PhD level. And we need to find a solution. When we do science right, we realize that the amount we don't know is vast, basically infinite. That can be terrifying, but it can also be exhilarating. We need to do, I think this is one of the things that as I've worked with students, I feel we need to do a little better job in mentoring students and young researchers and how to be productively stupid, meaning how do we recognize, embrace, and work with what we don't know? How do we learn from our mistakes in our simulations or our theorems? And in this sense, I'm meaning by feeling stupid, I mean that we're aware of what we don't know and what we don't yet understand. And I would argue that today in our lives right now as junior or senior, if we actually don't feel stupid from time to time, we're probably not really trying. We're probably narrowing our view too much, right? And so I feel that this is a normal, healthy part of being a researcher, is having this awareness of our own lack of knowledge, awareness of the vast things we don't know, and it actually can point us towards really interesting things and stimulate our curiosity. But we sometimes have to go through this emotional sense of failure occasionally when we're working through that. So how do we manage that? I don't have a wonderful answer, but I do think it's important for us to think about this. I can tell you how I think about it, but you may have better ideas. And I think that we want to find ways to encourage and help junior researchers through these steps. And even as we get further along in our career, we still could use reminders about these things. So I want to talk about the role of insecurity and confidence, kind of two opposite sort of sounding things. As I said before, we need to be aware of what we don't know and areas of technical difficulty for us, our weakness. What areas do we need to strengthen to be able to pursue this research? So we need to be aware of our strengths. We also, and so those are both important things. And so insecurity from a research point of view is when we're in a mindset where we emphasize our weaknesses. We just are kind of focusing on that. Maybe we've got a rejection from a paper, we've got a rejection from a grant, or we're just struggling with a step in our research. Confidence is when we emphasize our strengths. We're feeling great about everything. We're feeling really confident and able to move forward. Success requires balance between these two extremes, and the ability to not take either of them too personally, right? We want to be able to be in that position where we're able to constantly learn and progress. And I've gotten to know a number of the top theoretical researchers in our field and in adjacent fields. And some of them struggle with at least some area of knowledge that they eventually become an expert at some stage in their career. And that actually draws them in some ways to the things that interest them. And so let's talk a little bit about managing ups and downs in research. If we're doing it right, we should have both ups and downs. If we have no ups, then we need to mentoring guidance, or we need to go into another research area. Somehow we need to change things. If we have no downs, then we're probably not taking enough risks. We're not asking meaningful enough or hard enough questions. And we need to, again, to be careful to not take either of these personally. We need to learn from our ups and downs, including how to progress in both situations. How do we manage that? How do we talk ourselves through in a constructive way? How do we help our students get through those discouraged moments? I've had many students say to me, I don't think I belong here. I just don't think I'm going to be able to be as strong as these third or fourth year students. And that's exactly how those students felt at one time, at least in many cases. So we need to encourage others through this process and learn how we can better help them. And so I want to talk a little bit about responding to criticism and compliments. So one of the skills that's really important to learn is how to respond, how to learn what type of feedback to listen to and what type to ignore. We actually need a general sense of humility. This is not equal to insecurity. This is just our awareness of what we don't know and what we can learn from others. And we also need to have enough confidence that we can recognize that we can progress and achieve these things and we can move forward. So we should learn from critical feedback when possible, but not to take it personally. And sometimes one habit we get into is we look at some criticisms in a paper review or something, we begin to stack up in our mind all the things we're doing wrong, and sometimes it goes to the point where we really get negative about ourselves. Remember to not take these things personal and keep a balance as you review both your strengths and weaknesses. And also, importantly, we need to learn how to give useful feedback in our review processes. Try not to make it personal. Be professional. Make it useful so they can progress in the field. And I want to take an excursion now to talk about music a little bit. I think many of you know the great composer Jan Sibelius, a Finnish composer. Here's a picture of him in 1913. Well, I just want to talk a little bit about his experience that he had from criticism and compliments that he received. He was active at the time that Arnold Schoenberg was also a great composer, does beautiful stuff. And about this time, he had made some wonderful symphonies, all the way up to his 7th symphony. These are highly innovative, highly impressive. Just the creativity with which he developed his ideas is just path-breaking in these pieces. However, they're relatively tonal. Their tonal content is what we would recognize as, pretty singable, scale-based tonal pieces, although very rich tonality, more like the Wagner's Tristan and Isolde, where it's very complex tonality, but we can kind of recognize melodies and so on. Whereas Schoenberg was more focused on atonal approaches. And he would do very dissonant things where tonality would be absent for a lot of the piece. And sometimes people found this music very dissonant, but it certainly was considered very edgy stuff in the early 1900s. Now, personally, I like the music of both of these composers. They have a lot to offer. I think what happened is a lot of critics said very intense things about both of their works. Some critics would talk about how Jan Sibelius was just not very creative in his tonality was very simple. They ignored the fact that his formalism was richly original. Or they'd focus on Schoenberg's dissonance and would say that Sibelius was the answer, his way of doing it is the best of all. The thing that happened to him is that he got so caught up in all this critique, both positive and negative, as he was writing his 8th Symphony, he vacillated between feeling a failure and inability to move forward and an inability to meet the tremendously high expectations that some of his critics had. And he never was able to finish this symphony, which I know would have been amazing. He was literally stopped because he couldn't manage the positive and negative criticism. Now, I don't want to criticize him as a person because he was a brilliant composer, but I just want to raise this point that we have to balance this criticism and the critiques that we get in various forms and the compliments we get in various forms, and hold a middle course where we can be productive. I don't have a brilliant solution to how to do that. I just raise your awareness of this, but I think it's something we should think of a little bit more. Now, having said this, his body of work is still tremendous, and he's one of the most widely performed composers still to this day in concert halls. Okay, so let's now talk about another aspect of research. This is the role of critical thinking. Another thing it's a natural part of what we do. There are many ways that the critical thinking is discussed. There's many steps. We sometimes list steps. Those of us who actually try to use this in real life realize that it's really a complex cycle of many interacting steps, right, with a lot of feedback. But basically, we try to identify a question, a problem, a research goal. And then we identify the gaps in knowledge to be filled. Sometimes we do the gaps first to help us find these questions. But those kind of steps are involved. Then we gather needed information and data. This could be a good literature review. Probably it should include a literature review in the adjacent fields that are doing similar things. So my area in precision health, dynamic treatment regime, and reinforcement learning, I need to explore what's going on in econometrics, statistics, probability, engineering, especially industrial engineering, operations research, and computer science, to name a few. And those literatures are different. They don't often, but it's good to I'm not saying we do it all, but we should be in the habit of doing good literature review, as well as other ways of forming. Maybe with students, it might be, we need to learn an area of mathematics to be able to better tackle this problem. So we need to gather that, and so we may be gathering data in an actual experiment or doing simulations. We try to make sure that we have appropriate representativeness and diversity of perspectives. This could be when we're doing simulations, we try things that might break our method as well as things that might do well with our method. We also depending on what we're doing in science or out, we really want to make sure we have the multiple dimensions that are needed, maybe some that we're not even aware of, to fully understand our challenges. And some of the research and discovery process is to learn those things. We want to try to avoid bias. We want to try to check our errors through rigorous approaches. We analyze and evaluate, repeat above as needed, and importantly, we work with other people and get feedback through various means. And then we eventually get to the point where we distill the conclusions and disseminate the results, which include papers published and presentations at conferences and some iterations across those things. And so this is something we all know, but it's a very important skill. It's inherent to our fields. So let me talk a little bit more about it, though, because I think it relates to the rigor that we value in IMS culturally as a set of researchers. So our role in critical thinking, what is our responsibilities for critical thinking? We want to ensure rigorous critical thinking in our own fields, in the fields in IMS. Also, when we work with people in adjacent fields and people who might use our work, we want to assist those collaborators in other fields in the appropriate use and interpretation of our results and tools. We want to help connect our work to people outside of our discipline, too. Specific to statistics and the scientific method, statistics is essentially the science of the scientific method. So we're really supposed to be comfortable with this process as statisticians, although I personally feel that this is applicable to all of the fields that are involved in IMS. And the scientific method is another variation, a form of critical thinking. And so critical thinking in society, we're sort of helping with critical thinking with our collaborators. And as we learn from them, they're helping us. But in society, we're a little spoiled by our associations with researchers. In the rest of the world, critical thinking is not always a priority. And so we should probably, when we have the time and we have the inspiration, we should advocate for, I think, universal critical thinking skills and training for every sector of society. Maybe some of our work will be involved in some of those and maybe others, but I think we should be aware of the role of critical thinking in our disciplines and try to think about ways we can positively influence the critical thinking in society, because I feel many of us are aware that the decision-making that the world makes depends on the amount of and the type of critical thinking going on, right? And so this is very important. Okay, so I want to now move to who decides the important questions. And Michel Talleyrand received the 2024 Abel Prize, as you all know. I really like his advice, and honestly, it was part of the inspiration for some of the things I said so far today. But I really like what he says about some of these questions. Here's what he says. Sincerely work on the basic problem you can see right now, the problem you think matters. Don't worry about following the flock to the newest trend in town. Ask important and relevant questions. Be open to collaborations and mentoring. Humility is the juice of life. So here is one of the great thinkers of our day, mentions the importance of humility. I find that very interesting. And so I would kind of list some of his things that he highlights: curiosity, humility, collaboration, and mentoring. And so, one of the points I want to highlight is, as we look at what the important questions are, we're often asking ourselves, like, what are the more important questions? We should make sure that our own curiosity plays a large role in us deciding, because that's what he did, and I feel that curiosity is a light into our intelligence. It helps us know, and with students, their curiosity tells us what they potentially could be good at, right? It's a window into our own intelligence, even though we don't know it yet. The fact that we're pulled toward that suggests a resonance with those topics, right? So curiosity, I think, should be a guide because it helps us move towards where our strengths are. And so that's just something to consider. I think that that's related to his important comments. So now I want to completely shift topic. That idea was just to give us some sort of ideas to think about research. Hopefully, some of it was useful to at least help us ask questions that will help us each to proceed forward with our research with more enthusiasm, more vigor, and be able to help those that we work with, nurture, both junior research and other collaborators do the same. So let's talk about data science and artificial intelligence. This is a very big deal. Many of our disciplines play a role here, but our disciplines that we have represent other things as well, and there are other scientific areas outside, like physics and astronomy and other areas that touch on our field as well, but I just want to talk a little bit about data science and artificial intelligence briefly, because I'm fairly familiar with that area. So, and many of our disciplines are central to this. So what should we as IMS do about it? We've already had some talks in past presidents about this, and we should just be involved, right? Conferences and publications are one thing. I just want to mention that we have an ad hoc committee on machine learning and artificial intelligence, co-chaired by Xiang Lin and Andrew Gordon-Wilson at the New York University Courant Institute, and many of you on the committee are here. I just want to acknowledge that they're working on this question. They will have all the answers for us. I'm just kidding, but they'll help us make progress on this very difficult question, because I feel that we need to do a little bit more to be engaged, and part of it is there's so few of us compared to how many other people there are working in these fields. And it's very clear to many people outside of our field as well as us that we have a lot of unique contributions we can make from our perspective in our various fields, including we can bring unique perspectives of probability and inference about the real world. So one of the things that statistics is central to is taking our data and trying to figure out something that is true about the real world, not just about the data. Obviously, that's a really hard thing to do, right? And probability is foundationally critical to this. But I think this is something important. This is not a perspective that generally comes from people not in statistics and allied fields to statistics. And I feel that that's a lot that we have, something we have to offer from a perspective as well as our own individual skill sets. And also a question is, should we follow or lead? I think we are doing both now. There are actually individuals in IMS who are setting paths in both the theoretical and the applied sides of AI, and they're providing leadership. But I think we probably could lead more than we are. And so I don't have a solution to all of this. We're all grappling with this question. I really appreciate the ad hoc committees thinking about this and willing to help us think about this. And I just invite you to continue to think about this, because I think it's a very important thing. I want to say a little bit more about AI. And we all know that there's good and bad. AI, the bad things are it could take over the world and we would no longer have our own individual agency. That's very unlikely. Just as an AI specialist, it's really unlikely. At least for the next 6 months, I think it's highly unlikely. And it could surpass all human knowledge and creativity. There's AI tools, large language models that are developed to write music. I was a little nervous, and then I listened to some of this, and I said, I don't have anything to worry about. It's probably going to be another 100 years before it will really supplant. However, AI is very, very useful. There's a package I use in my own work that is able to take notes on a score with the instruments given and play the collection of notes to have it sound almost like a symphony orchestra. And this is done, the company that does, I won't tell you the company, but if you're curious, I'll tell you how to get hold of this software. But what they've done is throughout the 20th century, they took recordings of concert pieces, linked them to the scores, and they studied and matched the sounds until it can render the sound and match orchestra and the various things that instrumentalists do so it nearly sounds like humans. And it's been improving over the last few months. The first time I used it, I thought, well, that's way better than what I've done before. A couple months ago, I did it again, and my family said, that almost sounds like a real orchestra. So it's getting better and better, but it's not quite there. But there's other things that AI can do to assist us in our work. We know about AI and various versions of it that have been used for solving various types of interesting problems. And so I think that AI could be used to, so the bad things, let's continue with the bad things. Sorry, I was drifting here. It could also increase social inequities, biases, and contention. That's actually happened. Some of us know that the machine learning and Google and I shouldn't name anything, but social media has had some algorithms that literally encourage contention and rumor at the expense of fact. And so some people who measure these say there's been a societal change in some sectors of the world where people are less willing to look at other points of view, and they're more willing to chase rumors and interesting conspiracy theories and other things because of the directions that the links have been doing subtly over the last few. That's kind of scary. I'm not saying that's actually happening, but I think that it's not a trivial factor. I think a very important fear that I have is that AI could enable humans to stop growing intellectually and stop thinking for themselves. A lot of the calculations that we learn in arithmetic, we can do on our iPhone, right? We don't really need to do it ourselves. And I worry that people are going to rely more and more on things that supplant the intellectual, mental developments we need so we can stay lifelong critical thinkers. And that scares me almost more than anything else on here, because if we all lose that capacity, that will stop society's progress, I think, in its tracks. But what about the good, though? AI could help us do better with hard tasks. It already is doing that. It could actually help us learn better and more fully achieve our intellectual potential. So although it could take away our learning, we can also use it to target difficulties that are hard to discern and be able to strengthen people in areas that would help them. So it could be actually used to truly help. And it also could be used to help us become more fair and inclusive. This has to be a conscious effort. So it's what we do with AI that determines how good it is, I think, but it has tremendous potential. Okay, and so IMS researchers should be involved, they already are, but we should be involved in all aspects of AI for which our perspective can be helpful. Underlying theory, performance guarantees. I have a number of colleagues who develop AI for medical decision making, and they say that I'm really nervous because we have these test sets that we set aside and we have these other things, but I don't have any theoretical reason to believe that some of these things are right or an idea of the accuracy. And I know many of you are working on parts of these problems, conformal inference, for example, but there's things that are more fundamental to the actual modeling structure of deep learning that some of you are looking at as well that can help us gain performance guarantees. Posterior consistency being an example, but there's many other examples of increasing granularity. Applications, we need to be involved in those because some of them are complex and require more than just taking existing packages and apply them. We also can help with developing better algorithms. This is something where many of us work in different aspects of this, but it can help there. So my feeling is anything which does, could, or should involve probability, foundations, data analysis, or inference, IMS should be involved in. And it should be, a lot of these things should be involved, or I don't think artificial intelligence will move forward very well. And we may need to learn more in computer science and other areas. We may need to expand on this. In my lab, I have my students, in addition to take machine learning and data science courses, I have them, those who are interested, practice on some of the interviews that some of the big tech companies, Google, Amazon, give that test their programming skills. So they have to get these skills together, and there's online resources for that, and so far they've been successful. But there are many ways we can think about, I'm not asking that they become computer scientists, but ways that we can connect better to computer science by having a little more knowledge about some of these areas. So going forward, I just want to thank you all for your many important contributions to science, mathematics, society, and to IMS. I really want to thank you for the privilege of being able to be a small part of this very important work. It's really been a privilege and an honor for me, and I've really enjoyed the people and also the intellect that I've been able to observe. And also I want to offer you to please feel free to reach out to me and the other leaders of IMS with suggestions. Please let us know if you want to volunteer for something. We love to hear those, get those emails. Now, I'm not saying specific committees, but just volunteering generally. We like to carefully assign the committees to provide a rich representation, but if we know that you're interested in volunteering, that will help us. We would really appreciate that. And so I wish you all success and fulfillment in your careers, and this is all I have to say today. Before anybody leaves, I want to remind you all, those who've been asked to come down for the new Fellows and Travel Award winners, to come down as a group for the photo. Thank you. So.